The world we know was built over the remains of worlds that came before it. Roads cross forgotten settlements. Forests grow over ancient foundations, and mountains conceal chambers cut by hands that vanished thousands of years ago. Yet scattered among these lost landscapes, remarkable structures still rise above the ruins of their time. Their walls preserve unfamiliar designs, their stones carry traces of extraordinary workmanship, and their hidden spaces continue to reveal details no one expected to find. Some have clear histories, others remain surrounded by questions that centuries of research have only partly answered. Time has changed almost everything around them, but somehow, enough survived to keep their stories unfinished. Today, we journey through these ancient places and uncover the mysteries they have carried across thousands of years.
Located in present-day Ueda City, Nagano Prefecture, Japan, Ueda Castle was first built in 1583 by the warlord Sanada Masayuki. Archaeological excavations, historical military records, topographic surveys, and modern digital reconstructions have revealed that this was far more than a typical Sengoku period fortress. Despite its relatively modest size, Ueda Castle achieved something almost impossible. It successfully resisted Tokugawa armies twice, in 1585 and 1600, even when vastly outnumbered. Today, researchers continue to investigate how a fortress occupying only a fraction of the area of Japan's largest castles could repeatedly defeat one of the most powerful military forces of its era. Most military historians agree that castle size often correlates with defensive capability. Osaka Castle covered approximately 1 square kilometer, while Himeji Castle occupied a vast complex protected by multiple defensive rings. By comparison, Ueda Castle was significantly smaller. Yet in 1585, roughly 2,000 Sanada defenders held off a Tokugawa force estimated at more than 7,000 soldiers. 15 years later, during the events leading to the Battle of Sekigahara, a force of only 2,000 to 3,000 defenders delayed nearly 38,000 Tokugawa troops. The numbers alone present a mystery. Military simulations suggest that numerical superiority of that scale should normally overwhelm a fortress of Ueda's size. In many historical sieges around the world, defenders facing odds greater than 10 to 1 rarely succeeded for long. Yet Ueda repeatedly achieved what appears statistically unlikely. Researchers therefore began asking a deeper question. Was the castle's success primarily the result of brilliant leadership, or did hidden engineering features give the defenders advantages that modern observers still do not fully understand? The answer may lie beneath the visible ruins. One of the most remarkable discoveries emerged from detailed surveys of the castle's layout. Most visitors assume that a fortress is designed simply to keep enemies out, but Ueda appears to have been designed to manipulate enemy movement. Modern mapping reveals that attackers approaching the castle could not advance in a straight line. Instead, they were forced through a complex sequence of turns, elevation changes, narrow passages, and controlled entry points. Military engineers sometimes compare this concept to modern defense in depth, a strategy in which multiple defensive layers slow, divide, and exhaust an attacking force before it reaches its objective. The surprising part is that Ueda employed these principles centuries before the concept was formally studied. Computer analysis of reconstructed attack routes demonstrates that large formations repeatedly lost cohesion while advancing. Units could not maintain orderly ranks, commanders struggled to communicate across twisting pathways, and troops arriving at the front often became compressed into narrow bottlenecks. Similar effects can be observed in medieval European castles, yet Ueda appears unusually optimized for this purpose. Some researchers estimate that certain approach routes reduced the effective width of attacking formations by more than 70%. Numerical superiority became far less useful when thousands of soldiers were forced into narrow channels where only a small number could engage at once. How Sanada engineers calculated these effects without modern mathematics remains unknown. At first glance, Ueda Castle does not occupy an obviously superior natural position. Unlike mountain fortresses perched on inaccessible peaks, Ueda stands on relatively moderate terrain near the Chikuma River basin. This creates one of the castle's greatest engineering mysteries. If nature did not provide exceptional defences, where did those defences come from? Recent terrain studies suggest that the landscape surrounding the castle was heavily modified by human activity. Large earthworks, embankments, defensive slopes, trenches, and moats transformed the original environment into an artificial battlefield. Researchers using digital elevation models have identified irregular ground formations that do not appear natural. The scale of these modifications is impressive. Moving tens of thousands of cubic meters of soil without mechanized equipment would have required enormous labor resources. Comparable earth-moving projects in medieval Europe often demanded years of coordinated work by large populations, yet surprisingly few contemporary records describe the construction process. This absence of documentation has led some historians to wonder whether parts of the defensive system incorporated older fortifications that predated Sanada Masayuki's arrival. If true, Ueda may represent the evolution of the defensive knowledge accumulated across multiple generations, rather than the creation of a single architect. Another unresolved mystery concerns the castle's firing angles. Most original wooden towers and defensive structures no longer survive. As a result, archaeologists must reconstruct their positions using foundation remains and historical illustrations. When researchers model these structures digitally, a fascinating pattern emerges. Many locations appear positioned to create overlapping fields of fire. An attacker entering a particular corridor could potentially be targeted simultaneously from several directions. This concept resembles modern military principles of interlocking fire zones. What makes Ueda particularly interesting is the timing. The castle was built during a period when firearms were rapidly transforming Japanese warfare. Matchlock muskets, introduced from Portugal in the 16th century, were becoming increasingly important on battlefields across Japan. Some military historians believe Ueda may have been among the earliest Japanese castles specifically optimized for combined firearm and archery defense. If correct, this would place the fortress at the forefront of military engineering during a period of technological transition. Exactly how these firing networks operated remains uncertain because too much of the original architecture has vanished. Water has always been one of the most critical elements in castle design. Without reliable water supplies, even the strongest fortress eventually falls. Excavations have revealed evidence of sophisticated moat systems and drainage channels throughout Ueda Castle. The challenge is understanding how these systems function together. The region experiences significant seasonal variation. Heavy rainfall, snow accumulation, spring meltwater, and periodic flooding all influence water management. Yet historical accounts rarely mention major failures of the castle's defensive moats. Modern hydrological analysis suggests that engineers may have exploited subtle differences in elevation to regulate water flow naturally. Some channels appear positioned with remarkable precision. Even small errors in gradient could have rendered parts of the system ineffective. Researchers continue debating whether the builders relied solely on practical experience or possessed a more advanced understanding of hydrology than commonly assumed for the period. The lack of surviving technical documents makes definitive answers impossible. Perhaps the most overlooked mystery is not physical at all, it is informational. Historical records indicate that Tokugawa commanders repeatedly misjudged the strength of the Sanada defenders. This raises a critical question. How did a relatively small domain maintain such effective intelligence and deception capabilities? The Sanada clan became famous for espionage, misinformation, and strategic communication. Some historians suspect that hidden observation points, signal networks, and messenger routes connected the castle to surrounding territories. If these systems existed, they may have allowed defenders to monitor enemy movements with remarkable efficiency. Comparable communication systems elsewhere in the world often relied on signal fires, flags, relay stations, or coded messages. However, direct archaeological evidence remains scarce. What survives instead is the outcome: a pattern of military decisions by Tokugawa commanders that repeatedly underestimated the fortress. In modern terms, Ueda may have been as much an information processing center as a defensive structure. Perhaps the greatest mystery is the loss of the knowledge behind Ueda Castle itself. Historians know the fortress was highly effective, successfully delaying much larger armies with well-designed defenses, engineered terrain, and carefully planned firing zones. Yet no detailed manuals explaining these achievements have survived. This is not unique to Ueda. Many advanced techniques throughout history, from Roman concrete to medieval fortifications, have been lost over time. The evidence remains, but the instructions do not. What do you think was Ueda Castle's greatest secret? Its hidden engineering, its battlefield strategy, or a lost technology we have yet to rediscover? Let us know your thoughts in the comments below.
Vrelo is a late Roman imperial complex in eastern Serbia that holds one of the ancient world's most underrated engineering mysteries. How were Roman engineers able to construct a royal burial site with remarkable precision in a remote mountainous area? And why do some of the sophisticated technologies used there remain only partly understood today? The story of Vrelo entered modern archaeology during systematic excavations conducted in eastern Serbia during the late 20th century. Archaeologists uncovered the remains of a fortified imperial residence, ceremonial buildings, defensive walls, and one of the most remarkable royal mausoleums ever discovered in the Balkans. Evidence suggests that the complex was associated with Emperor Maximinus Dire, one of the rulers of the Roman Tetrarchy during the early 4th century AD. Yet, despite decades of study, many aspects of the site's construction, logistics, and funerary technologies continue to raise difficult questions. The first mystery involves location. Roman imperial residences were normally built near major cities, military centers, or strategic transportation routes. Vrelo stands apart. The complex occupies a relatively isolated area surrounded by rugged terrain in eastern Serbia. Constructing an imperial complex in such a location required enormous logistical coordination. Archaeological surveys indicate that the fortified enclosure covered more than 3 hectares and contained numerous monumental structures. Thousands of tons of stone, brick, timber, lime, and roofing materials had to be transported across difficult terrain. Modern engineers understand the materials used, but the organization behind the project remains difficult to reconstruct. No large-scale industrial staging areas have yet been identified nearby. No complete transportation network serving the site has been discovered. Yet, the finished complex displays the characteristics of a carefully planned imperial project. Similar logistical achievements can be seen at the Palace of Felix Romuliana, approximately 40 kilometers away, another imperial residence connected to the Tetrarchic period. The comparison suggests that Roman authorities possessed a regional construction system capable of mobilizing labor and resources on a scale far greater than many historians once believed. The second mystery concerns surveying and architectural precision. Excavations reveal carefully aligned walls, organized courtyards, defensive structures,
and ceremonial spaces constructed according to a unified architectural plan. Roman engineers are known to have used instruments such as the groma for alignment and the chorobates for leveling. However, maintaining geometric consistency across an entire complex built on uneven terrain required remarkable technical skill. Archaeological measurements show that many structures follow consistent orientations despite variations in topography. Similar precision can be observed in imperial complexes throughout the Roman world, yet Vrelo-Sharkamen presents a challenge because of its location. Modern surveyors working in mountainous terrain rely on advanced optical equipment, satellite positioning systems, and digital mapping technologies. Roman engineers achieved impressive accuracy without any of these tools. Exactly how they coordinated large-scale construction in such conditions remains only partially understood. The third mystery involves water management. Every Roman palace depended upon reliable access to water. Baths, kitchens, fountains, workshops, and residential quarters required constant supply. Archaeologists have identified evidence for hydraulic infrastructure at Vrelo-Sharkamen, including channels and water-related installations. However, the full system has never been completely reconstructed. This raises an important engineering question. A royal complex housing elites, servants, guards, and ceremonial functions would have required substantial quantities of water every day. Even modest Roman bath facilities could consume thousands of litres daily, yet the precise source capable of sustaining long-term operation remains uncertain. Some researchers suspect that portions of the hydraulic network remain buried beneath later deposits or outside the currently excavated area. Others propose that natural springs in the region were exploited more efficiently than previously assumed. Until additional evidence emerges, the true scale of the water system remains one of the site's unresolved technological puzzles. The fourth and perhaps most fascinating mystery centres on the royal mausoleum and the technology of cremation. This discovery transformed Sharkamen from an interesting imperial residence into one of the most significant archaeological sites in southeastern Europe. Archaeologists uncovered a monumental funerary complex containing cremated human remains and an extraordinary collection of gold jewellery. The treasure included necklaces, earrings, rings, pendants, and luxurious ornaments crafted with astonishing precision. Analysis of the artifacts revealed workmanship of exceptional quality, consistent with elite imperial production during the late Roman period. The cremation itself presents several unanswered questions. Roman cremation was not a simple process. To completely reduce a human body to calcined bone required temperatures that could exceed 800 degrees Celsius. Achieving and maintaining such temperatures demanded careful control of fuel, airflow, combustion chambers, and pyre construction. Experimental archaeology has demonstrated that successful cremation requires a highly organized sequence of operations and considerable technical knowledge. At Vrelo-Sharkamen, the remains indicate a cremation ceremony conducted with extraordinary sophistication. The bones were carefully collected after burning and deposited within a monumental funerary setting. This suggests not merely ritual activity, but a controlled technological process. Some researchers have compared the operation to high-temperature industrial procedures because maintaining consistent combustion over extended periods is remarkably difficult without extensive experience. The gold artifacts introduce an even deeper mystery. Several objects exhibit extremely fine decorative techniques involving tiny granules and delicate wire elements. Some gold wires measure fractions of a millimeter in thickness. Creating such features required advanced metallurgical knowledge, specialized tools, and highly skilled craftsmen. Modern microscopic analysis shows that Roman goldsmiths employed techniques including granulation, filigree, soldering, and alloy control. Yet, historians continue to debate the exact procedures used to join microscopic components without damaging surrounding structures. Even today, reproducing some ancient jewelry techniques requires laboratory conditions
and highly trained specialists. The comparison becomes even more remarkable when viewed alongside other famous treasures of the Roman world. Many pieces discovered at Vrelo Sharkamen rival the quality of jewellery recovered from imperial contexts in Italy, Egypt, and Asia Minor. The existence of such craftsmanship in a relatively remote Balkan locations suggests access to artisans connected to elite imperial workshops. Another unanswered question concerns the identity of the individual buried there. Many scholars believe the mausoleum may have belonged to a female member of the imperial family associated with Maximinus Dia. The richness of the grave goods supports this interpretation, yet definitive proof remains elusive. The result is a rare combination of historical, technological, and archaeological uncertainties centered on one of the most important funerary discoveries in the Balkans. The fifth mystery involves the speed of construction. Historical evidence indicates that the complex was likely built during a relatively brief period connected to the Tetrarchic era. This means planners had to coordinate architects, engineers, masons, metalworkers, labourers, and supply networks within a limited time frame. The Roman Empire certainly possessed immense resources. However, transforming a remote landscape into a fortified imperial centre required extraordinary administrative efficiency. Archaeologists can study the finished structures, but much of the organisational system responsible for creating them has disappeared. The workers, engineers and managers who made the project possible remain largely invisible in the archaeological record. The final mystery concerns abandonment. Despite its apparent importance, Vrelo Sharkamen did not continue functioning as a major imperial centre for centuries. Political instability, dynastic change, shifting military priorities, and broader transformations within the Roman Empire may all have contributed to its decline. Yet the exact sequence remains uncertain. Which mystery of Vrelo Sharkamen fascinates you the most? Let us know your theory in the comments below.
Matala Caves are located in southern Crete, Greece. Rising above the waters of Matala Bay is a honeycomb-like cliff containing dozens of artificial chambers carved directly into soft sandstone. Archaeologists have studied the site since the 19th century, and excavations have revealed that many of the caves were used during the Roman period, particularly between the 1st century BC and the 2nd century AD. Yet despite more than a century of investigation, researchers still cannot fully explain how ancient builders created such an extensive cliffside complex with the technology available at the time. The caves are often described as Roman tombs, but the reality may be far more complicated. Behind their simple appearance lies a series of engineering puzzles involving surveying, rock cutting, structural stability, and large-scale planning that remain only partially understood today. At first glance, Matala appears to be nothing more than a collection of random openings in a rock face, but closer examination reveals something very different. More than 60 artificial caves are distributed across a sandstone cliff overlooking the Mediterranean. Many contain multiple chambers, carved entrances, windows, benches, niches, and interconnected rooms. Some are positioned several meters above sea level, while others occupy locations that would have required dangerous access during construction. Creating a single chamber in rock is difficult enough, but constructing dozens of chambers across a vertical cliff face requires long-term planning, labour organisation, and engineering knowledge. Researchers estimate that thousands of cubic meters of sandstone were removed. Even relatively soft sandstone requires continuous cutting, shaping, and debris removal, and without modern machinery, every cubic meter would have been excavated manually using iron tools. This raises an obvious question: who coordinated such a project? No surviving inscriptions identify the engineers, and no construction records describe the work. The people responsible for transforming the cliff into a massive architectural complex remain unknown. The situation resembles other famous rock-cut monuments such as Petra in Jordan, the Ajanta caves in India, and the rock-hewn churches of Lalibela in Ethiopia. In every case, archaeologists can study the finished structures while knowing remarkably little about the engineering teams that created them. Perhaps the greatest technical mystery concerned the excavation process itself. Modern engineers examining the site face a fundamental problem. There are several possible ways to create chambers inside a cliff, but each method presents serious difficulties. If workers carved directly into the cliff from the front, they would have required extensive scaffolding. Building stable wooden platforms against a steep coastal rock face would have demanded careful planning and enormous quantities of timber. If workers approached from above using ropes, they would have needed advanced techniques for positioning labourers and removing excavated stone. If they combined both methods, the logistics become even more complicated. Archaeologists have identified tool marks throughout the caves, confirming that iron implements were used extensively. However, the exact sequence of excavation remains uncertain. Experimental archaeologists attempting to recreate ancient rock-cutting techniques have discovered that progress is far slower than most people imagine. Removing even a few cubic meters of stone can require hundreds of labour hours, and scaling that effort to the entire Matala complex suggests a massive investment of time and manpower. Yet no historical source explains how the work was organised. The cliff preserves the result, but not the process. One of the most overlooked mysteries involves geometry. Many chambers display surprisingly regular dimensions. Doorways align with interior spaces, niches appear deliberately positioned, and certain cave groups follow recognisable patterns rather than random placement. This implies some form of surveying. Today, engineers rely on laser measurements, digital models, and precise instruments. But ancient builders possessed none of these tools. Even so, they still had to answer critical questions. How far should each chamber extend into the rock? How could they avoid accidentally breaking into neighbouring chambers? How did they maintain alignment while excavating spaces that could not be fully observed from the outside? Researchers studying ancient construction have repeatedly encountered similar puzzles. The builders of the Egyptian pyramids maintained remarkable precision across millions of stone blocks. Roman engineers constructed aqueducts with gradients measured in centimetres per kilometre. The creators of underground cities such as Derinkuyu in Turkey excavated vast networks without modern surveying equipment. Matala may represent another example of sophisticated practical geometry whose exact methods have been lost. The traditional explanation identifies many caves as Roman burial chambers. Archaeological evidence certainly supports funerary use. Several caves contain features commonly associated with tombs, and artifacts discovered during excavations indicate burial activity. Yet some researchers question whether this explanation tells the entire story. Certain chambers possess layouts that appear unusually complex for simple tombs. Multiple rooms, carved benches, and enlarged interior spaces suggest that at least some caves may have served additional functions. They may have been temporary dwellings, storage facilities, religious chambers, or meditation spaces. The debate continues because physical evidence can support more than one interpretation. This uncertainty is not unique to Matala. Similar disagreements surround numerous ancient sites, including parts of Petra, Cappadocia, and various rock-cut settlements throughout the Mediterranean. The caves may represent a combination of functions developed over centuries rather than a single purpose. The sandstone cliff itself presents another puzzle because not all rock behaves the same way. Modern geological surveys reveal variations in density, fracture patterns, weathering resistance, and structural stability across coastal sandstone formations. Choosing the wrong location for excavation can lead to collapse. Yet, many Matala chambers have survived for nearly 2,000 years. This suggests that the builders understood far more about the rock than simple trial and error. Before carving each chamber, they likely evaluated the strength of the stone, the direction of natural fractures, the risk of roof failure, the effects of water infiltration, and the long-term stability of the cliff face. Modern mining engineers perform similar assessments using geological mapping, core samples, and structural analysis software, whereas ancient builders relied entirely on observation and accumulated experience. The fact that so many chambers remain intact indicates an impressive level of practical geological knowledge. The Mediterranean coastline is an aggressive environment. Salt crystallization, wind erosion, temperature fluctuations, and moisture gradually destroy exposed rock surfaces, and over centuries these processes can dramatically alter entire landscapes. Yet large portions of Matala remain recognizable after nearly 2 millennia. Scientists studying sandstone weathering have found that coastal erosion rates can vary significantly depending on mineral composition and environmental conditions. Even small differences in rock structure can determine whether a surface survives for centuries or disintegrates relatively quickly. This creates a fascinating question. Did the ancient builders intentionally select the most durable portions of the cliff, or were they simply fortunate? Some geological evidence suggests that specific sections of the sandstone formation possess superior structural characteristics. If the builders recognized these differences, they may have been making sophisticated engineering decisions long before geology became a formal science. Perhaps the most difficult mystery involves access. Many caves occupy positions that appear challenging even today. Modern visitors use pathways, stairs, and safety infrastructure, but ancient workers had none of these advantages. To excavate chambers several meters above ground, labourers would have needed scaffolding, rope systems, material transport methods, safety procedures, and communication systems. All of these technologies leave surprisingly little archaeological evidence. Wood decays, rope disappears, and temporary structures vanish. As a result, researchers can study the chambers themselves, but rarely the equipment used to create them. The same problem affects investigations at Petra, Cappadocia, and numerous cliffside monasteries throughout the ancient world. The structures survive while the engineering systems that enable their construction are almost entirely lost. What do you think was the most impressive achievement behind the Matala caves? The surveying, the excavation, or the cliffside engineering? Share your thoughts in the comments below. Tamagusuku Castle Ruin stands on a limestone hill overlooking the southeastern coast of Okinawa, Japan. Today, only fragments of its stone walls remain, surrounded by dense subtropical vegetation. Archaeologists believe the site was occupied between the 12th and 14th centuries, during the formative period of the Ryukyu Islands. Unlike many Japanese castles, however, Tamagusuku appears in historical records only briefly, and no surviving documents explain who designed it, how it was built, or why its engineering differs from many contemporary fortifications. Excavations conducted throughout the 20th century uncovered stone foundations, defensive walls, ceramics, and evidence of long-term occupation, but the most important discoveries raised more questions than answers. The deeper researchers study the ruins, the more they realize that Tamagusuku preserves clues to a sophisticated engineering tradition that remains poorly understood. The first puzzle begins with the castle's location. Tamagusuku occupies a strategic limestone ridge rising above the surrounding landscape. At first glance, this seems like a typical defensive choice. as throughout history, civilizations from medieval Europe to feudal Japan placed fortifications on elevated terrain to maximize visibility and defensive advantages. Yet Tamagusuku's position is unusually precise. Modern topographic analysis shows that the castle commands views of both inland approaches and large sections of the Pacific coastline. The builders selected a location that balances surveillance, defense, access to fresh water, and proximity to agricultural land, an optimization that normally requires extensive surveying. Today, engineers use satellite imaging, digital terrain models, and geographic information systems to identify ideal defensive locations, but the builders of Tamagusuku possessed none of these technologies. This raises a fundamental question. How did they evaluate the landscape so accurately? Researchers studying ancient Ryukyuan settlements have noted that many Gusuku castles occupy positions that appear mathematically efficient for visibility and defense. Similar patterns have been observed at sites such as Nakijin Castle and Katsuren Castle. The consistency suggests that the builders may have possessed surveying methods that have never been documented. No measurement tools, maps, or engineering manuals explaining these methods have ever been discovered. The most famous feature of Tamagusuku is its stone masonry. Unlike later Japanese castles that often used carefully cut stone blocks, Tamagusuku relies heavily on irregular limestone pieces fitted together with remarkable precision. Many sections were constructed without mortar, relying entirely on geometry, weight distribution, and friction. At first, this may not sound extraordinary, yet modern structural engineers recognize that dry stone construction can be surprisingly complex. Every stone influences the stability of the entire wall. Builders must understand load transfer, stress distribution, settlement behavior, and slope pressure, since a single misplaced stone can destabilize an entire structure. What makes Tamagusuku fascinating is that many wall segments have survived centuries of typhoons, earthquakes, humidity, and erosion. Okinawa lies within one of the world's most active typhoon regions, where powerful storms regularly generate winds exceeding 150 kilometers per hour. Heavy rainfall accelerates erosion and weakens foundations, yet despite these conditions, portions of the castle remain standing. The mystery becomes even more intriguing when compared with European medieval castles. Many European fortifications relied heavily on mortar to maintain wall integrity, while Tamagusuku achieved comparable durability using far less binding material. How its builders determined the optimal shape, placement, and weight distribution of thousands of individual stones remains unknown. One of the most surprising aspects of Ryukyuan castles is their apparent resilience to seismic activity. Japan experiences approximately 1,500 measurable earthquakes every year, and Okinawa itself is affected by regional tectonic activity associated with the complex interactions of the Philippine Sea Plate and Eurasian Plate. Conventional rigid structures often crack under repeated seismic stress, but dry stone structures behave differently. Modern earthquake engineering has demonstrated that certain stone systems can absorb and dissipate energy through microscopic movement between blocks. Instead of resisting every force directly, the structure flexes slightly and redistributes stress. Researchers studying ancient masonry have observed similar behavior at Machu Picchu in Peru and parts of the Inca Road network, leading some specialists to believe the walls of Tamagusuku may employ comparable principles. The problem is that there is no evidence indicating whether the builders intentionally designed for earthquake resistance. Were they applying sophisticated empirical knowledge accumulated over generations, or did seismic resilience emerge accidentally through centuries of trial and error? Without written records, the answer remains elusive. The castle was constructed primarily from Ryukyu limestone, a material formed from ancient coral reefs. This creates another puzzle. Limestone possesses both advantages and weaknesses. it is relatively easy to shape, but it is also vulnerable to weathering, chemical erosion, and structural fracturing. Many ancient civilizations struggled to preserve limestone structures for extended periods. Portions of the Egyptian pyramids, for example, suffered significant surface deterioration due to environmental exposure. Yet, some sections of Tamagusuku's walls remain surprisingly stable. Researchers have suggested several explanations. Perhaps the builders carefully selected stone with specific density characteristics. Perhaps they understood drainage patterns that minimize water accumulation. Perhaps they intentionally designed wall geometry to reduce stress concentrations. No theory has been conclusively proven. What is clear is that the builders achieved a level of long-term durability that exceeds what many would expect from coral-derived limestone exposed to centuries of subtropical weather. The walls of Tamagusuku contain stones weighing hundreds or even thousands of kilograms. Transporting such material presents a significant engineering challenge. Modern construction relies on cranes, trucks, hydraulic equipment, and precision lifting systems. Medieval Europe used draft animals, winches, and extensive labor forces, while the builders of the Ryukyu Islands worked within a very different technological environment. No direct evidence survives showing how the stones were moved. Researchers have proposed several possibilities. Wooden rollers may have been used, earthen ramps could have facilitated transport uphill, lever systems might have amplified human strength, and temporary wooden frameworks may have supported lifting operations. However, archaeological excavations have uncovered little evidence supporting any single method. The challenge becomes even more impressive when considering the rugged terrain surrounding the castle. Moving multi-ton stones across uneven limestone landscapes would have required careful planning and coordination. The engineering solution remains one of Tamagusuku's greatest mysteries. Every successful fortress requires reliable access to water, a necessity that becomes especially important during sieges. Yet no large river passes directly through Tamagusuku's hilltop location. Researchers believe the inhabitants relied on a combination of rainfall collection, natural springs, and carefully managed drainage systems. The exact design of these systems remains uncertain because much of the original infrastructure has disappeared. What survives suggests a sophisticated understanding of hydrology. The castle's layout appears designed to channel runoff away from critical structures while preserving valuable water resources, following principles similar to those used in modern stormwater engineering. The mystery lies in how accurately the builders understood local rainfall patterns without modern meteorological data. Okinawa experiences intense seasonal precipitation, often exceeding 2,000 millimeters annually, and managing such volumes requires effective drainage planning. Evidence indicates that Tamagusuku's builders solved this problem centuries before modern engineering emerged. Some archaeologists believe Tamagusuku served more than a military function. Across the Ryukyu Islands, many Gusuku sites appear connected to sacred spaces, ritual areas, and religious traditions. Certain alignments within Tamagusuku have led researchers to speculate that spiritual considerations influenced its design. The castle overlooks important landscape features and occupies a position that may have held ceremonial significance long before fortifications were constructed. If true, this creates another engineering mystery. The builders would have needed to satisfy multiple requirements simultaneously, including defense, visibility, access to resources, structural stability, and religious symbolism. Modern architects often struggle to optimize so many variables at once, yet ancient builders appear to have achieved exactly that. Whether this reflects advanced planning methods or generations of accumulated knowledge remains unknown. What do you think? Were the builders of Tamagusuku simply masters of experience? Or did they possess engineering knowledge far more advanced than history currently recognizes? Let us know your thoughts in the comments below. Starocell is one of the most astonishing engineering mysteries of the ancient world. Hidden among the hills of central Bulgaria, about 140 kilometers east of Sofia, this massive Thracian temple complex has survived for more than 2,300 years. Built during the 4th century BC, possibly under the rule of the powerful Thracian king Soothes III, the site contains some of the largest ritual structures ever created by the Thracians. What makes Starocell extraordinary is not merely its age, but the level of engineering knowledge preserved in stone. Massive blocks weighing several tons were transported across difficult terrain. A circular sacred enclosure more than 240 meters in diameter was constructed with remarkable precision. And most astonishing of all, the builders created a gigantic stone dome that continues to stand after centuries of earthquakes, weathering, and human activity. The temple raises a question that archaeologists still cannot fully answer. How did a civilization often described as tribal achieve engineering results that rivaled some of the most sophisticated stone builders of the ancient Mediterranean? Although local people had known about the mound for centuries, the true importance of Starocell was revealed only in the year 2000, when archaeological excavations led by Georgi Kitov uncovered a monumental Thracian cult complex hidden beneath the landscape. What emerged was one of the largest and most elaborate Thracian religious sites ever discovered, and with every new excavation came new mysteries. The first mystery begins long before construction. The temple contains enormous granite blocks, some weighing several tons. Transporting such material today would require heavy machinery, yet the builders of Starocell had no engines, cranes, steel cables, or modern vehicles. Researchers believe the stone may have been transported from quarries located kilometers away. Even a relatively modest 5-ton block presents a significant logistical challenge. Experimental archaeology has shown that moving such weights using only wooden sledges and human labour requires careful route preparation, precise coordination, and large work crews. The challenge becomes even greater when considering elevation changes. The terrain surrounding Starocell is far from flat, and every additional degree of slope dramatically increases the force required to move heavy loads. The builders clearly possessed a sophisticated understanding of logistics, yet no written records explain how the operation was organised. Like the builders of Stonehenge, they left behind the result but not the instructions. The greatest engineering puzzle at Starocell lies inside the temple itself. At the centre of the complex stands a monumental chamber covered by a massive stone dome constructed using carefully arranged stone courses. More than 2 millennia later, much of the structure remains intact. At first glance, the dome appears simple. In reality, it represents one of the most difficult architectural challenges in the ancient world. A stone dome is fundamentally unstable during construction because every block exerts force not only downward, but also outward. If those forces are not perfectly balanced, collapse becomes inevitable. Modern engineers solve this problem using mathematical calculations, structural modelling software, reinforced concrete, and steel support systems. The Thracians had none of these tools, yet somehow they succeeded. The dome was built using a corbelled technique in which each successive ring of stones projects slightly inward relative to the layer below. Over time, the opening narrows until it can be closed at the top. The principle sounds straightforward, but the execution is extraordinarily difficult. Each stone must be positioned with remarkable precision. If the inward projection is too large, instability increases. If it is too small, the dome cannot close properly. Small cumulative errors become catastrophic as height increases, Engineers studying ancient corbelled structures have demonstrated that deviations of only a few centimeters can dramatically alter stress distribution throughout the structure. What makes Starocell remarkable is that the builders achieved this precision without laser measurements, modern surveying instruments, or structural calculations. Even more intriguing is the durability of the design. Bulgaria lies within a region influenced by seismic activity from the Balkan and Anatolian tectonic systems, and throughout the last 2,000 years numerous earthquakes have affected the region. Yet the dome endured. Why? One possibility is that the builders understood structural behaviour through generations of accumulated practical experience. They may not have possessed mathematical formulas, but they understood which proportions worked and which failed. Another possibility is that the design itself contains geometric relationships that naturally distribute stress efficiently. This phenomenon appears elsewhere in the ancient world. The treasury of Atreus in Greece, constructed around 1250 BC, contains a corbelled dome nearly 14.5 metres high that remains standing today. The builders of Newgrange in Ireland created a similar structural solution more than 5,000 years ago. In Peru, Inca stonework demonstrated extraordinary resistance to seismic forces despite the absence of mortar. Starocell belongs in this same category of ancient engineering achievements that appear deceptively simple but conceal sophisticated structural knowledge. The mystery is not that the dome exists. The mystery is that it still exists. Surrounding the temple is a massive circular wall measuring approximately 240 meters in diameter. Creating such a circle sounds easy on paper, but it is not. Maintaining geometric consistency across hundreds of meters requires accurate surveying methods, and even minor measurement errors become increasingly visible as the circle expands. Modern surveyors use total stations, GPS equipment, and digital mapping software. The Thracians relied on ropes, stakes, and human observation. Yet the enclosure displays a level of planning that suggests considerable geometric knowledge. How this knowledge was acquired remains uncertain. Several researchers have suggested that elements of the temple may have been aligned with significant solar events. Ancient civilizations frequently integrated astronomy into religious architecture. The Great Pyramid of Giza exhibits remarkable cardinal orientation. Newgrange is aligned with the winter solstice sunrise, and Chichen Itza creates famous shadow effects during equinoxes. Starocell may represent a Thracian version of the same phenomenon. If true, the builders were not merely architects, they were also observers of the sky. The extent of this knowledge remains debated. Which Starocell mystery fascinates you the most? The massive stone dome, the astronomical alignments, or the lost engineering knowledge behind it all? Let us know your thoughts in the comments below.
Migvimevi Monastery is a medieval monastic complex carved into the limestone cliffs of western Georgia. Perched above the Farila River Valley near the town of Kiachura, it appears at first glance to be just another remote mountain monastery. Yet hidden within its caves and stone walls lies a collection of engineering mysteries that continue to challenge archaeologists, architects, geologists, and conservation scientists. The greatest mystery is not why the monastery was built in such an inaccessible location. The real mystery is how medieval builders managed to transform a dangerous cliffside cave system into a stable religious complex that has survived more than 7 centuries of earthquakes, erosion, humidity, and environmental change. The story of Mugvimevi entered modern scholarship through archaeological and historical investigations conducted during the 19th and 20th centuries. Located in the Imereti region of Georgia, the monastery was known locally for centuries, but systematic studies revealed that much of the complex had been integrated directly into natural limestone formations. What researchers initially believed to be a simple cave monastery turned out to be a sophisticated combination of natural geology and engineered architecture. The first mystery concerns construction itself. The monastery was built against a steep limestone cliff that rises dramatically above the valley floor. Even today, transporting construction materials to the site requires considerable effort. During the 13th century, builders had no cranes, trucks, powered lifting equipment, or modern scaffolding systems, yet they successfully moved thousands of kilograms of stone, timber, roofing materials, plaster, pigments, and water to elevations that remained challenging even for modern workers. This problem becomes more puzzling when compared with other famous cliffside religious complexes. The cave monasteries of Cappadocia in Turkey were largely excavated from relatively soft volcanic tuff. The monasteries of Meteora in Greece were supplied using ropes and baskets suspended from towering sandstone pillars. Mgvimevi, however, occupies a narrow limestone environment that combines the difficulties of both systems. Archaeologists can observe the finished result, but the exact logistics network used by medieval builders remains unknown. No contemporary engineering records survive to explain how construction materials were transported and assembled with such precision. The second mystery involves geological engineering. Natural caves rarely possess the shape required for permanent human occupation. Most contain unstable ceilings, irregular chambers, and unpredictable fracture networks. Yet the spaces incorporated into Mgvimevi demonstrate evidence of deliberate modification. Builders expanded chambers, reshaped passages, and integrated architectural features into existing rock formations without triggering catastrophic collapse. Modern engineers rely on computer simulations, geological surveys, laser mapping, and structural analysis to evaluate the stability of excavated spaces. Medieval builders possessed none of these tools. Nevertheless, the monastery has remained standing for more than 700 years. This suggests an empirical understanding of rock mechanics that was far more sophisticated than historians once assumed. Some chambers appear to have been expanded within meters of natural fracture zones, yet they remain remarkably stable. Researchers still cannot fully explain how builders identified which sections of limestone could be safely removed and which had to remain untouched. The third mystery concerns seismic survival. Georgia lies within a tectonically active region, influenced by the collision between the Arabian and Eurasian plates. Historical records document numerous earthquakes throughout the Caucasus. Many medieval structures across the region suffered severe damage or complete destruction. Mgvimevi survived. Architectural studies suggest that the monastery benefits from an unusual relationship between built structures and natural rock. Instead of functioning as a completely independent building, parts of the monastery behave almost like extensions of the cliff itself. Some walls appear to distribute stress into the surrounding limestone rather than resisting seismic forces alone. This hybrid natural-artificial structure may have created a primitive form of earthquake resistance. Whether this effect was intentionally engineered or accidentally discovered remains unknown. The fourth mystery involves environmental control. Cave environments are notoriously difficult places to preserve organic materials. Humidity fluctuations, condensation, mineral deposits, biological growth, and temperature changes normally destroy fragile surfaces over time. Yet Mgvimevi has maintained stable interior conditions for centuries. Measurements from comparable limestone cave systems indicate that underground temperatures often remain within a narrow range throughout the year, sometimes varying by only a few degrees Celsius, despite extreme seasonal changes outside. Researchers suspect that natural ventilation channels within the cliff may create a self-regulating airflow system. These hidden pathways could remove excess moisture while maintaining stable temperatures. However, the complete ventilation network has never been fully mapped. The cave may contain environmental mechanisms that are still poorly understood. The fifth mystery concerns architectural precision. Religious architecture in the Orthodox Christian tradition follows highly structured spatial principles. Churches are normally aligned according to symbolic orientations and geometric relationships. Constructing such spaces inside irregular caves presents enormous challenges. Despite the limitations imposed by natural rock formations, the main church at Mugvimevi exhibits surprisingly consistent proportions. Wall alignments, ceiling transitions, and liturgical spaces demonstrate planning that appears incompatible with the constraints of the surrounding geology. Achieving such accuracy without modern surveying instruments would have required exceptional technical skill. The methods used by medieval builders to establish geometric control inside a complex cave environment remain largely speculative. The sixth mystery involves hidden passages and unexplored spaces. Archaeologists have identified secondary chambers, narrow corridors, and inaccessible recesses throughout the monastery complex. Some may have served as storage areas, refuges, workshops, or monastic cells, while others remain unexplored. Despite advances in ground-penetrating radar and 3D mapping, large parts of the Mugvimevi cave system remain difficult to study because of structural and conservation concerns. As a result, researchers still cannot fully understand how the monastery functioned at its peak. The seventh and perhaps greatest mystery concerns the preservation of the monastery's medieval frescoes. This mystery has attracted increasing attention from conservation scientists because the survival of these paintings appears almost improbable. The frescoes have endured for centuries despite exposure to environmental conditions that normally destroy wall paintings. Humidity, airborne particles, mineral salts, microorganisms, and temperature fluctuations represent constant threats to painted surfaces. In many medieval sites across Europe and the Near East, frescoes have faded dramatically or disappeared entirely, yet significant portions of the artwork at Mugvimevi remain visible. The science behind fresco preservation is extremely complex. Traditional frescoes are created by applying mineral pigments onto wet lime plaster. As the plaster cures, calcium hydroxide reacts with carbon dioxide from the atmosphere to form calcium carbonate. This process locks pigments into the wall itself, creating extraordinary durability. However, successful preservation requires stable environmental conditions. Excess moisture can dissolve salts. Drying cycles can produce cracking. Biological growth can destroy pigment layers. Researchers studying comparable medieval frescoes have found that even small fluctuations in relative humidity can accelerate deterioration. In some heritage sites, annual restoration efforts are required simply to slow the damage. The fact that Mugvimevi's paintings survived for centuries raises a remarkable question. Did medieval craftsmen possess specialized knowledge of materials that modern science still does not fully understand? Microscopic analyses of medieval plasters from various Georgian monuments have revealed carefully selected mixtures of lime, sand, mineral aggregates, and local additives. Some formulations exhibit exceptional resistance to moisture penetration. Others demonstrate unusual mechanical stability. It is possible that the artisans responsible for Mugvimevi employed regional techniques optimized through generations of experimentation. Even more intriguing is the possibility that the cave itself participates in preservation. Natural limestone acts as a chemical buffer, helping regulate humidity and atmospheric chemistry. The cave environment may continuously stabilize conditions around the frescoes. If true, the paintings represent not merely an artistic achievement, but part of a larger environmental engineering system, created through the interaction of geology, architecture, and material science. Modern conservation laboratories can analyze pigment composition, plaster structure, mineral content, and microclimatic conditions. Yet no single explanation fully accounts for the remarkable state of preservation observed in parts of the monastery. The survival of the frescoes appears to result from a combination of factors so complex that researchers are still attempting to separate them centuries later.
Beneath modern Guangzhou in southern China lies the buried remains of a palace more than 2,000 years old. What archaeologists discovered was not merely a royal residence, but an engineering system so sophisticated that some of its construction methods remain unexplained today. The ruins of the palace of the Nanyu Kingdom were discovered during urban construction projects in Guangzhou in the 1990s. Excavations revealed palace foundations, stone structures, ancient wells, waterways, gardens, and one of the most advanced hydraulic systems ever found from early imperial China. Among all discoveries at the site, none surprised archaeologists more than the vast underground water management network hidden beneath the palace complex. The Kingdom of Nanyu existed between 203 and 111 BCE, a period when much of the world still relied on relatively simple water collection systems. Yet, beneath the palace, researchers uncovered carefully engineered stone channels, drainage networks, wells, reservoirs, and artificial ponds connected through a coordinated hydraulic design. The challenge becomes apparent when examining the local environment. Guangzhou receives approximately 1,700 to 2,000 millimeters of rainfall annually, making it one of the wettest major regions in China. Heavy seasonal rains can quickly flood low-lying areas, and without proper drainage, large architectural complexes would suffer severe water damage. Yet evidence suggests the palace managed water remarkably efficiently. Excavated channels maintained consistent gradients that allowed water to flow naturally without causing erosion. Even today, civil engineers recognize that controlling water movement over large areas requires careful calculations of slope, flow velocity, and drainage capacity. The mystery is simple. How did engineers over 2,000 years ago achieve this level of precision without modern surveying equipment? Comparable hydraulic achievements can be found in Roman aqueducts or the water systems of Petra in Jordan. Yet Nanyu's engineers operated independently and developed solutions specifically adapted to the humid subtropical climate of southern China. The palace appears less like a residence and more like a giant machine designed to control water. One of the most unexpected discoveries was the remains of a royal garden dating back more than 2 millennia. Archaeologists identified artificial ponds, islands, waterways, and carefully planned landscape features. Scientific analysis of pollen, seeds, and preserved plant remains indicates that the garden contained numerous species selected intentionally rather than occurring naturally. At first glance, this might appear to be merely decorative. However, maintaining such a garden in a tropical environment presents enormous challenges. Water levels fluctuate, sediment accumulates, plants require different moisture conditions, mosquito populations can become uncontrollable, and stagnant water quickly becomes unhealthy. Modern landscape architects often use computer modeling to predict water circulation and environmental stability. Yet Nanyu's builders created a system that appears to have functioned effectively, using only natural hydraulic principles. Some researchers suggest the waterways may have simultaneously served aesthetic, climatic, and drainage purposes. Moving water could help regulate temperature while preventing flooding during heavy rainfall. If correct, the garden was not simply a display of wealth but a carefully engineered environmental system. Excavations uncovered numerous wells distributed throughout the palace complex. Many remain remarkably well preserved despite centuries of flooding, changing groundwater levels, urban development, and natural erosion. This durability raises important engineering questions. Groundwater exerts constant pressure on underground structures, and over time, poorly designed wells collapse as surrounding soil shifts or water weakens supporting materials. Yet many Nanyue wells retained their structural integrity for more than 20 centuries. Researchers found sophisticated brick and stone arrangements designed to distribute pressure evenly throughout the structure. Some wells display construction techniques suggesting that builders understood how groundwater interacted with soil layers. Today, geotechnical engineers use complex mathematical models to predict these effects. Ancient Nanyue engineers obviously lacked such tools, yet their practical solutions proved extraordinarily effective. The exact methods used to determine well placement and structural design remain unknown. The Pearl River Delta is not an easy place to build. The region contains soft sediments, fluctuating water tables, and unstable ground conditions that challenge modern construction projects even today. Yet the palace stood on this landscape for generations. Excavations revealed foundation systems that appear specifically adapted to local soil conditions. Multiple layers of construction materials were used beneath important structures, and drainage networks prevented excessive water accumulation near foundations. What makes this particularly fascinating is the absence of written engineering manuals explaining how these decisions were made. Modern engineers rely on geological surveys, soil testing, and computer simulations, while Nanyue builders relied on observation, experience, and methods now lost to history. The success of their foundations suggests a sophisticated understanding of local geology that archaeologists still struggle to fully reconstruct. Numerous stone components found throughout the palace exhibit surprisingly high levels of workmanship. Blocks were shaped, aligned, and installed with a degree of accuracy that required careful planning, and transporting these stones presented additional challenges. Some stones likely weighed several tons. Moving such materials across soft delta terrain would have required coordinated labor, specialized equipment, and logistical planning. The mystery is not whether ancient workers could move heavy stones, as civilizations around the world achieved similar feats. The mystery is how consistently Nanyue builders maintained construction standards across a large complex while operating in a humid environment that rapidly degrades building materials and infrastructure. Without surviving records, the construction process remains largely speculative. One of the greatest frustrations for archaeologists is that most of the palace's wooden superstructure has disappeared. Wood survives poorly in southern China's climate. High humidity, insects, fungal decay, and centuries of environmental exposure destroyed much of what once stood above the foundations. As a result, researchers know far more about what lay beneath the palace than what rose above it. Questions remain about how tall the buildings were, how roofs were supported, how structural loads were distributed, and how resistant the buildings were to storms and typhoons. The surviving foundations indicate that the architecture above may have been significantly larger and more complex than current reconstruction suggests. Unfortunately, many answers vanished with the wood itself. Perhaps the most fascinating mystery is not the palace itself, but the people who designed it. The kingdom of Nanyue existed for less than a century before being absorbed into the Han Empire in 111 BCE. Despite its relatively short lifespan, it produced a palace featuring advanced hydraulic engineering, sophisticated drainage systems, durable foundations, large-scale landscaping, and carefully planned urban infrastructure. Such achievements normally require generations of accumulated technical knowledge. This raises a profound historical question. Where did this expertise originate? Some historians argue that Nanyue inherited engineering traditions from the Qin dynasty. After the collapse of Qin rule, military leaders, administrators, craftsmen, and engineers may have migrated south and brought technical knowledge with them. Others suggest that local Yue populations already possessed highly developed environmental engineering skills adapted to the subtropical conditions of southern China. If true, much of the palace's success may have resulted from combining northern imperial knowledge with indigenous expertise. A third possibility is even more intriguing. Nanyue may have served as a technological crossroads where multiple engineering traditions merged and evolved into something uniquely suited to the Pearl River Delta. The problem is that historical records are limited. We see the channels, we see the wells, we We see the foundations and we see the results. But we know almost nothing about the individuals who conceived, calculated, organized, and supervised these projects. No surviving engineering manuals describe their methods. No detailed construction records explain their decisions, and no names of master engineers have been preserved. The creators of one of ancient China's most impressive engineering complexes have effectively disappeared from history. What do you think? Were the engineers of Nanyu simply masters of observation and experience? Or did they possess technical knowledge far more advanced than history has given them credit for? Let us know your thoughts in the comments below.
Fort La Prée is a coastal fortress on the French island of Ile de Ré that preserves one of the most overlooked engineering mysteries of early modern military history. Built between 1625 and 1630, on the edge of the Atlantic Ocean, the fortress was designed to withstand artillery bombardment, saltwater corrosion, unstable coastal ground, and centuries of violent storms. Nearly 400 years later, much of the original structure still survives. The mystery is not simply how the fortress remained standing. The real mystery is how 17th century engineers achieved such extraordinary geometric precision, structural durability, and defensive efficiency without modern surveying equipment, reinforced concrete, computer modelling, or industrial machinery. The story of Fort La Prée begins on the western coast of France on Ile de Ré, an island strategically positioned near the important Atlantic port of La Rochelle. Historians have long known about the fortress, but detailed architectural surveys conducted during restoration projects in the 20th and 21st centuries revealed unexpected levels of engineering sophistication hidden within its walls. Laser scanning, structural analysis, and archaeological studies showed that many parts of the fortress were built with a precision that continues to surprise military historians and engineers. One of the first mysteries concerns the fortress' survival against one of the most destructive environments on Earth. Modern coastal engineers recognize that seawater is extremely damaging to stone structures. Salt crystals penetrate pores within masonry, expand during moisture cycles, and gradually fracture building materials from within. Studies conducted on Atlantic coastal structures show that marine weathering can destroy exposed stone within a few centuries if construction methods are inadequate. Yet Fort La Prée has remained standing for nearly 400 years, despite constant exposure to ocean winds, humidity, and salt spray. The question is simple: how did 17th century builders create masonry capable of surviving conditions that challenge even modern structures? Researchers examining historical mortars discovered sophisticated mixtures of lime, aggregates, and carefully selected local materials. Some sections of the fortress display unusual resistance to deterioration compared with contemporary coastal structures. Laboratory analyses suggest that long-term chemical reactions within the mortar may have strengthened the material over time. Similar phenomena have been observed in Roman marine concrete, which continues to puzzle scientists because it sometimes becomes stronger after centuries of exposure to seawater. Although Fort La Prée does not use Roman concrete technology, the comparison raises an intriguing possibility that early engineers has possessed practical knowledge of durable construction techniques that are only partially understood today. Another mystery involves the foundations. The fortress was constructed on relatively unstable coastal terrain where heavy masonry structures would normally face settlement problems. Modern engineers solve such challenges using soil surveys, geotechnical drilling, computer simulations, and advanced foundation systems. None of these technologies existed in the 17th century, yet the builders successfully supported thousands of tons of stone walls, bastions, gun platforms, and defensive structures. Surveys indicate that the foundations extend farther and distribute loads more effectively than many historians originally expected. The precise methods used to evaluate ground stability remain largely undocumented. Some historians believe military engineers developed empirical techniques through generations of experience constructing fortifications across Europe. However, the absence of detailed technical records means that the exact calculations and procedures remain uncertain. The third mystery involves the fortress's drainage system. Water is one of the greatest enemies of military architecture. Rainwater trapped within walls can weaken mortar, destabilize foundations, and accelerate structural decay. Engineers at Fort La Prairie incorporated hidden drainage channels beneath courtyards and within defensive structures to remove excess water efficiently. Modern laser surveys reveal that these channels maintain remarkably consistent gradients. Even slight errors in slope could have caused standing water and long-term damage. Achieving such precision today would be straightforward with laser levels and electronic instruments. The builders of Fort La Prairie relied entirely on manual measurements, ropes, wooden instruments, and geometry. The accuracy they achieved remains impressive even by modern standards. The fourth mystery concerns logistics. Fort La Prairie required enormous quantities of stone, timber, lime, and metal. Historians estimate that major 17th century fortifications often involved moving thousands of tons of materials over difficult terrain. The challenge becomes even greater on an island separated from the mainland by strong tides and unpredictable Atlantic weather. Without steam engines, cranes, trucks, or mechanized lifting equipment, workers transported and positioned massive building materials with remarkable efficiency. Historical records document the construction effort, but provide limited information about the specific techniques used to lift, align, and place heavy stones. Similar questions surround many large historical engineering projects. The builders clearly possessed practical solutions, yet much of that technical knowledge was never fully recorded. The greatest mystery of Fort La Prairie, however, involves the astonishing geometric precision of its bastion design. This mystery lies at the heart of the fortress. Unlike medieval castles, which relied on high vertical walls, Fort La Prairie belongs to a new generation of military architecture developed in response to gunpowder artillery. Cannons had transformed warfare. Tall castle walls became vulnerable targets. Military engineers responded by creating low-profile fortresses with angled bastions capable of resisting bombardment while providing overlapping fields of fire. The effectiveness of such fortifications depended entirely on geometry. Every wall angle, every bastion projection, and every defensive line had to be positioned with extraordinary accuracy. A small error could create a blind spot where attackers could approach without being exposed to defensive fire. A miscalculated angle could weaken the entire defensive system. Modern military architects use computer simulations to model lines of sight and ballistic coverage. 17th century engineers possessed none of these tools. Yet when modern researchers analysed surviving bastion fortifications throughout Europe, including Fort La Prairie, they discovered geometric layouts that closely match sophisticated mathematical principles. The bastions at Fort La Prairie were designed so that defenders positioned on one wall could protect adjacent walls with crossfire. This created overlapping defensive zones that minimized vulnerable areas. The concept appears straightforward today, but implementing it across an entire fortress required extensive geometric planning. Laser mapping has revealed that many angles remain remarkably consistent despite centuries of repairs and environmental damage. In some sections, deviations are measured in only fractions of a degree. Such precision raises a difficult question. How did engineers achieve this level of geometric accuracy without modern instruments? One possible answer lies in advanced surveying methods inherited from Renaissance military science. European engineers of the 16th and 17th centuries increasingly applied geometry, trigonometry, and mathematical planning to fortress construction. However, surviving documents rarely provide enough detail to reconstruct the complete process. The challenge becomes even more impressive when scale is considered. Maintaining geometric precision across a fortress measuring hundreds of meters requires controlling cumulative errors. Modern surveyors use total stations, GPS systems, and digital mapping tools because small mistakes can multiply rapidly over distance. Engineers at Fort La Prairie achieved comparable results using simple optical devices, measuring chains, compasses, and mathematical calculations performed entirely by hand. Comparisons with other famous bastion fortresses reveal similar mysteries. The star forts, designed by engineers such as Sébastien Leprest de Vauban, later demonstrated extraordinary geometric sophistication across Europe. Some fortresses covered dozens of hectares while maintaining carefully calculated defensive relationships between every wall and bastion. Fort La Prairie represents an earlier stage in this evolution, making its precision even more remarkable. Perhaps the most fascinating aspect is that the fortress geometry was not merely theoretical. It functioned in real combat conditions. Defensive systems depended on precise lines of fire, visibility, communication, and artillery placement. Any significant geometric errors would have been exposed immediately during military engagements. The fortress therefore serves as a full-scale demonstration of engineering knowledge that worked in practice rather than merely on paper. Was the geometric precision of Fort La Prairie the result of mathematical genius, lost surveying techniques, or engineering knowledge that modern history has underestimated?
At 3,050 meters above sea level in Peru's Sacred Valley, Machu Colca sits among windswept mountains where oxygen levels are roughly 35 to 40% lower than at sea level. Archaeologists believe it was an Inca storage complex. Yet, the deeper researchers investigate, the more it resembles an engineering system designed with a level of environmental knowledge that remains difficult to explain. Located near Chinchero in the Cusco region of Peru, Machu Colca was identified through archaeological surveys of Inca infrastructure scattered throughout the Sacred Valley. The site became increasingly important as researchers realized its connection to the vast Inca network of roads, terraces, and storage facilities that once supported one of the largest empires in the Americas. The greatest mystery of Machu Colca is simple. Why would an empire deliberately build major storage facilities nearly 4 kilometers above sea level? Modern logistics generally place warehouses near transportation routes, population centers, or agricultural regions. Machu Colca appears to violate all three principles. Transporting food uphill requires enormous labor, temperatures fluctuate dramatically, and weather conditions can become severe. By modern assumptions, this should have been an inefficient location. Yet the Inca chose it intentionally. The explanation may lie in an extraordinary understanding of microclimates. At 3,150 meters, temperatures are significantly lower than in nearby valleys. Nighttime temperatures can approach freezing even when lower elevations remain relatively warm. Combined with constant mountain winds, these conditions create a natural preservation environment. Researchers studying Inca storage systems have found that high-altitude colcas, or storage structures, often occupy locations with carefully selected airflow patterns. Wind passing through openings could remove moisture while cool temperatures slowed bacterial growth and reduced insect activity. Today, modern food preservation relies heavily on controlling three factors: temperature, humidity, and airflow. Remarkably, Machu Colca appears to have optimized all three without electricity, refrigeration, or mechanical ventilation. Some studies of Inca storage complexes suggest that maize stored in favorable conditions could remain usable for years. Potatoes processed into chuno, a freeze-dried product created through repeated freezing and dehydration cycles, could last even longer. What remains difficult to explain is how the Inca identified these precise environmental conditions. No surviving documents describe atmospheric measurements, and no instruments equivalent to thermometers or hygrometers have been discovered. Yet they repeatedly selected locations that modern environmental engineers would recognize as naturally efficient preservation zones. When researchers compare Machu Colca to medieval European storage systems of roughly the same era, the contrast becomes striking. Many European granaries relied primarily on thick walls and elevated floors. The Inca, by contrast, appear to have integrated entire mountain landscapes into their storage strategy. In effect, the mountain itself became part of the machine. How they developed such sophisticated environmental knowledge remains one of the site's greatest mysteries. The storage structures at Machu Colca may represent something even more remarkable than simple warehouses. They may have functioned as a form of passive refrigeration centuries before the scientific principles behind cooling systems were formally understood. Modern refrigeration works by removing heat, and at Machu Colca, nature performed the same task. Cold nighttime air descended through the mountain landscape. Daily wind cycles continuously circulated fresh air through storage areas. Low atmospheric pressure reduced moisture retention. Combined together, these factors created conditions that naturally slowed food spoilage. Engineers analyzing passive cooling systems today often seek exactly these environmental advantages. The difference is that modern architects use computer simulations, while the Inca had only observation. The question is not whether the system worked. The archaeological evidence suggests it did. The real question is how they learned enough about climate behavior to design it. Some researchers estimate that the Inca state maintained thousands of storage structures across its empire. Such a network would have required centuries of accumulated environmental knowledge. The scale suggests deliberate planning rather than accidental success. Although Machu Colca is less famous than Machu Picchu, it still displays many characteristics associated with Inca engineering. Stone blocks were shaped to fit together with remarkable precision. No mortar was required, yet many joints remain intact despite centuries of earthquakes, rainfall, and temperature fluctuations. Modern structural engineers understand why these designs work. Walls with slightly inward slopes improve stability, trapezoidal openings distribute stress more effectively, and interlocking stones allow structures to absorb seismic energy. What remains unclear is how these solutions were discovered. The Andes are among the most seismically active regions on Earth. Peru experiences thousands of earthquakes every year. Over generations, the Inca may have learned through observation which design survived and which failed. Yet the sophistication of the final results continues to impress engineers. Even today, some modern earthquake-resistant concepts mirror principles visible in Inca architecture. The storage complex itself is impressive, but the system supporting it may be even more astonishing. The Inca Empire stretched approximately 4,000 kilometers along the Andes and, at its peak, governed an estimated 10 to 12 million people. Unlike many ancient civilizations, the Inca had no wheeled transport for cargo. They possessed no horses and used no draft animals comparable to oxen. The largest pack animals available were llamas, capable of carrying only around 20 to 30 kilograms. Yet vast quantities of food moved across mountains, deserts, valleys, and high plateaus. The empire maintained more than 40,000 kilometers of roads. Messenger runners known as chasqui relayed information across enormous distances. Storage facilities such as Machu Colca formed critical nodes in this network. Some historians compare the system to a pre-industrial supply chain operating on a continental scale. Food collected in one region could be redistributed hundreds of kilometers away. Military campaigns depended upon it, and remote populations survived because of it. The entire network functioned without written alphabets, wheeled freight transport, or mechanized equipment. Few ancient logistical systems achieved comparable efficiency under such difficult geographic conditions. Machu Colca was not built in isolation. It existed within a landscape transformed by human design. The surrounding region contains agricultural terraces, water management systems, roads, and carefully positioned settlements. Terracing reduced erosion while increasing agricultural productivity. Drainage systems controlled runoff during seasonal rains, and roads linked highland communities to lower valleys. Together, these features reveal an advanced understanding of environmental engineering. Modern satellite imagery has shown that many Inca constructions were positioned with extraordinary attention to topography. Rather than forcing the landscape to conform to architecture, the architecture adapted to the landscape. This philosophy reduced maintenance requirements and increased long-term resilience. Even after centuries of abandonment, many Inca structures continue to function remarkably well. Perhaps the most intriguing question concerns the site's true purpose. Archaeologists generally classify Machu Colca as a storage complex, and the name itself supports that interpretation. Yet some features raise questions. Its strategic position offers extensive views across surrounding terrain. Its connection to transportation routes suggests administrative importance, and its scale exceeds what some researchers would expect for a simple local facility. Could it have served additional functions? Possibly. It may have operated as a regional distribution center, a state-controlled logistics hub, a monitoring station, or even a location connected to ceremonial activities associated with agriculture and food security. At present, definitive answers remain elusive. What do you think? Was Machu Colca simply an ancient storage complex, or evidence of a sophisticated environmental engineering system far ahead of its time? Share your thoughts in the comments below.
Kazanlak, central Bulgaria. Beneath a modest earthen mound lies a small circular tomb that contains some of the most astonishing paintings ever created in the ancient world. More than 2,300 years after they were painted, their colours remain visible, their details remain sharp, and the technology behind them remains only partially understood. The Thracian tomb of Kazanlak is often described as an archaeological treasure. In reality, it may be one of the greatest technological mysteries of ancient Europe. The tomb was discovered accidentally in 1944 when soldiers digging defensive positions near the city of Kazanlak broke into an underground chamber. What they found stunned archaeologists. Inside was an almost perfectly preserved Thracian burial monument dating to the late 4th or early 3rd century BC, decorated with extraordinary murals unlike anything previously known from Thracian civilization. Today the tomb is recognized as a UNESCO World Heritage Site, yet many of its engineering secrets remain unresolved. The first mystery appears before anyone even studies the paintings. The burial chamber consists of a narrow corridor leading into a circular domed room approximately 2.65 meters in diameter. The dome itself was constructed from carefully arranged bricks that create a nearly perfect geometric structure. This may not sound extraordinary until one considers the period. The tomb was built more than 2 centuries before the Roman Empire reached its architectural peak. There were no laser levels, no precision surveying instruments, no modern engineering calculations, and no steel reinforcement. Yet the dome has survived over 23 centuries despite earthquakes, seasonal temperature fluctuations, soil pressure, and moisture exposure. Modern engineers studying ancient masonry structures often note that even minor geometric errors can significantly weaken a dome. The remarkable symmetry of Kazanlak suggests that Thracian builders possessed surveying techniques far more sophisticated than traditionally assumed. How did they establish such accuracy underground? No surviving manuals provide an answer. The second mystery involves the materials themselves. The paintings were not applied directly onto raw brick surfaces.
builders first created carefully prepared plaster layers designed to receive pigments. For over 2,300 years, these surfaces have resisted cracking, separation, and deterioration. Modern conservation studies indicate that the plaster contains highly refined lime mixtures combined with carefully selected aggregates. The quality of preparation appears unusually high for the period. The challenge is that ancient lime technology was far from simple. Producing durable plaster requires precise control of firing temperatures, slaking procedures, mixing ratios, curing conditions, and application timing. Small mistakes can dramatically reduce long-term stability. Yet the Kazan-Lak surfaces continue to support paintings that have survived longer than many medieval artworks. Researchers still debate whether organic additives, plant extracts, proteins, or other stabilizing materials may have been incorporated into the mixture. The complete recipe remains unknown. The greatest mystery of Kazan-Lak is undoubtedly its artwork. The circular chamber contains scenes depicting a Thracian nobleman and his wife participating in a ceremonial banquet. Around them are servants, musicians, horses, chariots, and ritual figures. Above them, the curved dome becomes a continuous narrative painted with astonishing precision. At first glance, the paintings appear merely beautiful. Closer examination reveals something far more remarkable. They survived. Many ancient murals have vanished entirely. Others survive only as fragments. Even masterpieces from later periods often suffer severe fading, pigment loss, salt damage, biological growth, or surface detachment. The Kazan-Lak paintings remain visible after more than 23 centuries. This raises a fundamental technological question. How? Scientific analysis has identified pigments based largely on naturally occurring minerals. Red tones appear linked to iron oxides. Black pigments likely derive from carbon-based materials. White areas were created using lime-rich compounds. These materials were known throughout the ancient Mediterranean. What remains difficult to explain is the extraordinary stability achieved by the Thracian painters. Modern microscopic examinations suggest that pigments were applied through carefully controlled processes, rather than simple decorative painting. Some areas reveal multiple layers, indicating a sophisticated understanding of colour preparation and surface interaction. Researchers have compared aspects of the technique with fresco traditions later perfected in Roman and Renaissance art. The comparison is surprising because the Kazan-Lak murals predate many of the most famous surviving fresco cycles by centuries. Even more impressive is the artist's mastery of visual effects. Human faces display subtle emotional expressions. Horses appear dynamic and energetic. Clothing folds create convincing depth. Shading techniques generate three-dimensional illusions on curved surfaces. These achievements required more than artistic talent. They required technical knowledge. The painters understood how pigments behaved on wet plaster, how colours changed during drying, how mineral particles interacted with binders, and how environmental conditions affected long-term durability. Such knowledge could only have emerged through generations of experimentation. Yet almost none of that knowledge was written down. One of the most puzzling scientific questions concerns pigment preservation. Exposure to humidity, oxygen, microorganisms, and chemical reactions normally causes gradual degradation. In many ancient sites, colours disappear entirely after only a fraction of Kazan-Lak's lifespan, yet numerous pigments remain identifiable today. Some conservation scientists suspect that the microenvironment inside the tomb played a critical role. Others emphasize the exceptional quality of the plaster. Still others point toward the purity of the mineral pigments themselves. The truth may involve all three factors. What makes the puzzle particularly fascinating is that modern laboratories can identify the surviving materials, but reconstructing the exact ancient manufacturing process remains far more difficult. The final product survives, the production knowledge does not. Another technological puzzle involves preservation conditions. Underground structures typically face constant threats from groundwater, humidity fluctuations, fungal growth, and temperature changes. Yet the tomb protected its paintings for more than 23 centuries. This suggests that the builders may have understood local geology and drainage conditions at a surprisingly advanced level. The burial mound itself likely acted as a natural environmental buffer. Temperature changes underground occur far more slowly than at the surface. Moisture movement can also be influenced by careful site selection and construction techniques. Modern climate-controlled museums achieve similar objectives using sensors, ventilation systems, and computer monitoring. The Thracians achieved remarkable preservation without any of these technologies. Perhaps the greatest mystery is not the tomb itself, it is the disappearance of the knowledge behind it. The builders understood geometry, structural engineering, material science, and environmental control. The painters understood pigments, chemistry, optical effects, and preservation techniques. The craftsmen understood how to transform ordinary minerals into colors capable of surviving for millennia. Yet almost none of their technical explanations remain. What do you think was the greatest secret behind Kazanlak's remarkable preservation? The pigments, the plaster, or the engineering itself? Share your thoughts in the comments below. Southern Okinawa, Japan. Hidden among limestone ridges and dense subtropical vegetation, the ruins of Osato Castle reveal a mystery that has puzzled archaeologists for decades. Long before modern surveying instruments existed, someone built a fortress whose walls seem perfectly matched to the landscape itself. The question is simple. How did they understand the terrain so precisely? The ruins of Osato Castle, known locally as Osato Gusuku, have been documented since the 19th century and studied extensively during 20th century archaeological surveys of Okinawa's ancient Gusuku fortifications. Excavations uncovered stone walls, defensive terraces, ceramics, and evidence linking the site to the rise of the Ryukyu kingdom between the 12th and 15th centuries. The greatest mystery surrounding Osato Castle is not its walls, but the land beneath them. Unlike many medieval castles built by imposing artificial defences onto the landscape, Osato appears to have been designed around the terrain itself. Steep limestone cliffs, natural depressions, sinkholes, ridges, and elevated plateaus were incorporated into the fortress so effectively that some archaeologists describe the site as a collaboration between human engineering and natural geology. Today, military planners use satellite imagery, LiDAR scans, digital elevation models, and geographic information systems to identify optimal defensive positions. Yet the builders of Osato had none of these technologies. The limestone landscape of southern Okinawa belongs to the Ryukyu limestone formation, a geological layer created hundreds of thousands of years ago through coral reef deposition. Over time, rainwater dissolved portions of this limestone, creating a complex karst environment filled with hidden cavities, steep slopes, sinkholes, and irregular rock formations. For modern engineers, mapping such terrain requires advanced surveying equipment, and even small errors can produce blind spots in defensive planning. Yet the walls of Osato consistently occupy positions that maximize visibility, while minimizing vulnerable approaches. Researchers who have compared Ryukyuan castles with European hill forts note that many castles in medieval Europe relied heavily on massive walls, because their builders could not always exploit terrain with such precision. At Osato, however, natural obstacles often performed the defensive role that elsewhere required enormous amounts of masonry. This raises an intriguing question. Did Ryukyuan builders possess sophisticated methods of terrain analysis that have been lost to history? No written manuals explaining their techniques have survived. Constructing a fortress on limestone presents serious challenges. Limestone is highly susceptible to weathering, and water slowly dissolves the rock, creating underground voids and fractures. Modern engineers often conduct extensive geological testing before constructing large structures on karst terrain. Yet the builders of Osato somehow selected areas capable of supporting defensive walls that survived for centuries. The region receives approximately 2,000 millimeters of rainfall annually, and Okinawa sits within a zone frequently affected by typhoons, earthquakes, and seasonal storms. Under such conditions, structural instability should be common. Nevertheless, significant sections of Gusuku walls across Okinawa have remained standing for hundreds of years. Some researchers argue that ancient builders possessed a practical understanding of geological stability that rivaled the empirical knowledge used by many modern field engineers. The question remains unanswered. How did they identify stable foundations without drilling equipment, geological surveys, or modern soil analysis? Another mystery emerges when examining the castle's construction materials. Many of the stones used in Ryukyuan fortifications were quarried locally, yet evidence for large-scale quarrying operations remains surprisingly limited. At first glance, the walls seem simple, but closer inspection reveals remarkable complexity. Individual stones were selected and positioned to conform to irregular terrain. Instead of forcing the landscape to accommodate the walls, the builders shaped the walls around the landscape. This approach resembles certain construction techniques seen at sites such as Machu Picchu, where stones were fitted to natural contours with extraordinary precision. The comparison is not perfect, as Machu Picchu employed finely dressed polygonal masonry, whereas Osato used different stoneworking traditions. Yet both sites demonstrate an engineering philosophy centered on adaptation rather than domination of nature. How these stones were transported across rugged slopes without wheeled vehicles capable of handling such terrain remains a subject of debate among archaeologists. One of the most overlooked mysteries involves water management. Typhoons regularly bring intense rainfall to Okinawa, and modern measurements show that some storms can deliver hundreds of millimeters of rain within a single day. For the hilltop fortress, uncontrolled runoff can be catastrophic as water erosion weakens foundations, destabilizes walls, and triggers landslides. Yet many Ryukyuan castles endured these conditions for centuries. Researchers believe the builders intentionally integrated natural drainage channels into their designs. Rainwater appears to have been guided through existing depressions, fissures, and karst formations, rather than being trapped within the settlement. Modern landscape engineers often rely on hydrological modeling software to predict water flow, but the builders of Osato somehow achieved effective drainage through observation alone. Their methods remain unknown. Another remarkable feature involves line-of-sight control. From elevated sections of the castle, observers could monitor large portions of the surrounding landscape. Agricultural zones, transportation routes, and neighboring territories were visible from strategic vantage points. Recent digital terrain analyses conducted at various Okinawan Gusuku sites have revealed that many were positioned in locations offering exceptionally efficient visual coverage. This is more than coincidence. Identifying such locations without modern topographic maps would require extensive knowledge of the surrounding environment. Some historians believe generations of accumulated local knowledge allowed builders to understand the landscape at an extraordinary level, while others suggest the existence of surveying practices that left little archaeological evidence. Either explanation points toward a surprisingly advanced tradition of environmental intelligence. The Ryukyu Islands stretch across more than 1,000 kilometers between Japan and Taiwan. Maintaining political control over such distances required communication. Some researchers have proposed that Gusuku fortresses may have functioned as nodes within a broader warning network. Elevated locations could have enabled visual signaling using fire, smoke, or reflective surfaces. Comparable systems existed elsewhere in the ancient world. The Romans operated beacon chains across frontier regions. Ancient China developed extensive signal tower networks, and medieval Europe used hilltop beacons to warn of invasion. Could Okinawa have possessed a similar system? Direct evidence remains scarce, but the geographic positioning of several castles continues to fuel speculation. Perhaps the most fascinating mystery is not how Osato Castle was built, but why the knowledge behind it disappeared. The builders demonstrated expertise in geology, hydrology, logistics, defensive planning, and environmental adaptation. They understood how to transform natural terrain into a military advantage, selected stable ground without modern geological science, controlled water without computer simulations, and positioned fortifications with an accuracy that continues to impress researchers today. Yet detailed construction manuals have never been found. No surviving texts explain how the terrain was surveyed, no records describe the engineering calculations, and no documents reveal how generations of builders acquired their knowledge. The stones remain, but the methods do not. What do you think? Was Osato Castle built through generations of experience, or does it preserve evidence of forgotten engineering knowledge? Let us know your theory in the comments below.
Dresnik is a Roman archaeological site in western Kosovo that preserves one of the most puzzling technological mysteries of the late ancient world. How did a remote provincial settlement acquire the resources, engineering knowledge, and artistic capabilities normally reserved for the great imperial centres of the Roman Empire? The site lies near the modern village of Dresnik, approximately 20 kilometers west of Peja in Kosovo. At first glance, it appears to be just another Roman ruin scattered across the Balkans. Yet beneath the soil lies evidence of architecture, defensive engineering, and artistic craftsmanship so sophisticated that archaeologists continue to debate the true status of the settlement. The greatest mystery is not that Romans built impressive structures here. The real mystery is why such extraordinary technology appeared in a location that should never have possessed it. The modern discovery of Dresnik occurred during archaeological investigations in the early 21st century. Excavations revealed the remains of a monumental Roman complex dating primarily to the 4th century AD, during the turbulent decades when the Roman Empire struggled to maintain control across its vast territories. What researchers expected to find was a provincial villa. What emerged instead was something far more complicated, a fortified complex featuring massive walls, ceremonial halls, advanced heating systems, imported luxury materials, and some of the finest mosaic floors ever discovered in Kosovo. The first and perhaps greatest mystery concerns the mosaics themselves. Archaeologists uncovered extensive mosaic floors covering large sections of the complex. This alone was remarkable. Throughout the Roman world, mosaic decoration was expensive. Wealthy homeowners often reserved mosaics for reception halls, dining rooms, or baths. Even luxurious villas rarely decorated every important space with elaborate mosaic artwork. Yet at Dresnik, large portions of the complex appear to have been adorned with intricate geometric designs created from thousands upon thousands of carefully cut tesserae. The scale creates an immediate problem. To manufacture mosaic floors of this quality required specialized craftsmen. Every tessera had to be quarried, cut, transported, sorted by color, and placed according to a carefully planned design. Studies of Roman mosaics elsewhere suggest that experienced workshops could lay only a limited area per day while maintaining geometric accuracy. Some estimates indicate that a skilled mosaic team might complete only a few square meters of highly detailed work daily. This means the floors at Dresnik likely required months or even years of coordinated labour. The mystery deepens when the geometry is examined. Many Roman mosaics contain repeating patterns. Repetition may look simple, but maintaining perfect symmetry across large surfaces is an engineering challenge. Modern builders rely on laser levels, measuring tapes, and digital planning software. Roman craftsmen possessed none of these tools, yet the geometric patterns discovered at Dresnik remain remarkably consistent across large floor surfaces. Small measurement errors should have accumulated over distance, causing visible distortions. Instead, the designs retain their proportional relationships with surprising precision. How was this achieved? Some researchers suggest the use of grids, cords, wooden measuring rods, and chalk guidelines. Yet no surviving documentation explains the exact methods employed by mosaic workshops operating in provincial regions of the empire. The technical knowledge required to coordinate hundreds of thousands of tesserae remains only partially understood. The mosaics of Dresnik rival decorative programs found in elite sites such as Mediana in Serbia or Felix Romuliana, both associated with imperial power. Why a settlement in western Kosovo possessed comparable artistic capabilities remains one of the site's great puzzles. The second mystery involves the monumental hall discovered within the complex. Archaeologists identified an aula, or ceremonial hall, measuring approximately 22 meters long and 11 meters wide. Such dimensions are not typical for ordinary rural estates. Large audience halls were symbols of authority. They were spaces where governors received visitors, officials conducted administration, and powerful individuals displayed status. The question is simple: who required such a building? The surrounding region was not Rome. It was not Constantinople. It was not Thessalonica. These cities served as major political and economic centres. Dresnik occupied a comparatively remote position within the empire, yet the architecture suggests access to resources on a scale far beyond what historians would normally expect from a local landowner. This has led some scholars to propose that the complex may have served a governmental or imperial function. Others argue that it belonged to an exceptionally wealthy aristocrat. Neither explanation fully resolves the problem. The architecture appears too ambitious for a normal villa, yet too isolated for a major administrative capital. The third mystery concerns the enormous defensive walls. Excavations revealed fortifications approximately 3.7 meters thick in some areas. Circular towers may have reached diameters between 10 and 16 meters. These are not symbolic structures. They represent serious military engineering. Defensive walls require enormous investments in labor and materials. Thousands of tons of stone had to be extracted, transported, shaped, and assembled. Every meter of wall represented a commitment of manpower, food supplies, engineering knowledge, and logistical coordination. But what exactly were these defences protecting? If the complex was merely an agricultural estate, the fortifications seem excessive. If it functioned as a military centre, evidence for large garrisons remains limited. If it served an imperial role, historians still struggle to explain why such an important facility was established here. The contradiction remains unresolved. The fourth mystery involves Roman heating technology. Evidence indicates the presence of a hypercourse system, one of the most advanced heating technologies of the ancient world. A hypercourse functioned by circulating hot air beneath raised floors and within wall cavities. The system transformed buildings into giant thermal machines capable of maintaining comfortable indoor temperatures even during harsh winters. Constructing a hypercourse required precision engineering. Brick pillars had to support elevated floors. Furnace chambers needed carefully controlled airflow. Heat distribution required sophisticated understanding of architecture and thermodynamics, even if Roman engineers did not possess modern scientific terminology. The challenge becomes even greater when fuel consumption is considered. Large hypercourse systems demanded continuous supplies of wood. A single heated complex could consume enormous quantities of fuel over the course of Winter season. Maintaining such a system required organized forestry, transportation networks, storage facilities, and skilled operators, yet many details remain unknown. Researchers can reconstruct the physical structures, but they cannot fully explain how daily operations were managed. Questions about fuel procurement, maintenance schedules, labor organization, and thermal efficiency remain subjects of ongoing debate. The fifth mystery concerns long-distance logistics. Luxury materials discovered at the site suggest access to trade networks extending across the Balkans and beyond. Marble, decorative stone, glass, metal objects, and specialized construction materials had to travel considerable distances before reaching Dresnik. Modern transportation systems make such movements seem ordinary. In the 4th century, it was anything but ordinary. Moving heavy cargo over land required wagons, draft animals, roads, bridges, laborers, and administrative coordination. Roman logistics were impressive, but the presence of high-status materials in a relatively remote location raises difficult questions about the site's economic importance. Why would merchants and officials devote so many resources to supplying this settlement? No surviving written record provides a definitive answer. The 6th mystery may be the most exciting of all. Many archaeologists suspect that only a fraction of the ancient settlement has been excavated. Geophysical surveys suggest additional structures remain buried beneath surrounding fields. Scattered finds indicate a larger urban landscape than originally imagined. This possibility changes everything. If the visible remains represent only the central core of a much larger settlement, then current interpretations may be fundamentally incomplete. The monumental hall, luxury mosaics, and defensive walls could be components of a forgotten Roman centre, whose true extent remains hidden underground. Entire districts may still await discovery. Workshops, administrative buildings, residential quarters, storage facilities, and religious structures could lie beneath the landscape, invisible to the naked eye. Srebrenik Fortress is a medieval stronghold in northeastern Bosnia and Herzegovina, perched on a limestone outcrop about 500 meters above sea level. First mentioned in historical records in 1333, it remains one of the best preserved fortresses in the Balkans. Yet beyond its military history lies a technological mystery that continues to challenge archaeologists, engineers, and historians alike. How did medieval builders construct, supply, and maintain a heavily fortified stone citadel on a nearly isolated rock summit, using only the tools and knowledge available more than 6 centuries ago? The fortress attracted modern archaeological interest through historical surveys conducted during the 19th and 20th centuries. Restoration efforts revealed multiple construction phases hidden beneath later modifications. Excavations uncovered defensive walls, towers, gateways, cisterns, and structural foundations built directly into the natural bedrock. These discoveries led researchers to an important conclusion. The fortress was not simply built on a mountain. It was carefully engineered into the mountain itself. The greatest mystery begins with the location. Srebrenik stands atop a steep rocky pinnacle separated from the surrounding terrain by deep natural slopes. Even modern visitors often wonder how builders transported construction materials to the summit. The walls contain thousands of tons of limestone blocks, mortar, timber supports, roofing materials, and defensive structures. Modern engineering projects facing similar terrain would typically rely on cranes, heavy lifting machinery, reinforced access roads, and detailed geological surveys. Medieval builders possessed none of these advantages, yet the fortress walls reach several meters in height and thickness while conforming precisely to the irregular contours of the rock beneath them. Archaeologists estimate that constructing even a modest medieval fortress could require thousands of cubic meters of stone. A single cubic meter of limestone weighs approximately 2,400 kilograms. Transporting such quantities up a steep mountain without mechanized equipment would have required an extraordinary logistical operation. Historical records provide little information regarding the techniques used. Whether builders employed temporary wooden ramps, pulley systems, scaffolding networks, or methods now lost to history remains unknown. The mystery becomes even more fascinating when compared with other European fortresses. Many castles were built on elevated terrain, but relatively few occupy rock formations as isolated and difficult to access as Srebrenik. The challenge was not merely building walls. The challenge was delivering an entire construction industry to the summit. One of the most overlooked technological achievements at Srebrenik lies beneath the visible walls. The fortress has survived centuries of weather, warfare, earthquakes, and abandonment. Such durability suggests that its foundations were carefully integrated into the geology of the mountain. Limestone presents both advantages and problems. It is strong under compression but vulnerable to erosion, cracking, and water infiltration. Modern engineers conduct extensive geological testing before placing heavy structures on fractured limestone. Medieval builders lacked modern instruments, yet they somehow identified stable sections of bedrock capable of supporting massive defensive walls. Excavations have revealed areas where the natural rock appears intentionally modified. Builders cut, leveled, and shaped portions of the summit before construction. In some locations, walls appear locked directly into carved sections of bedrock, creating a unified structural system rather than separate architectural elements. The precision required for such work is remarkable. A poorly positioned wall could shift under its own weight, particularly during freeze-thaw cycles common in the Balkan climate. Winter temperatures often move above and below freezing, causing water trapped within rock fractures to expand and contract repeatedly. This process destroys many historical structures, yet significant portions of Srebrenik remain standing after more than 600 years. How medieval engineers evaluated geological stability without modern surveying equipment remains one of the fortress's greatest unanswered questions. Every fortress faces the same fundamental challenge: water. For a mountain fortress, the challenge becomes exponentially more difficult. Military historians estimate that a single person requires several liters of water daily for drinking and food preparation. Horses require significantly more. During prolonged sieges, access to water often determined whether a fortress survived or surrendered. Srebrenik's position creates a serious logistical puzzle. The fortress stands high above surrounding water sources, and transporting water manually would have been impractical during wartime. Archaeologists have identified cistern systems designed to collect rainwater, but debate continues regarding whether these reservoirs alone could support a large defensive garrison. Some researchers propose that sophisticated rainwater harvesting systems existed throughout the complex. Others suggest the possibility of deeper storage structures or now lost supply mechanisms. Similar questions have emerged at mountain fortresses across Europe and the Middle East, where surviving remains often reveal of only fragments of ancient hydraulic systems. The engineering challenge is enormous. A medieval garrison of merely 100 people could require hundreds of litres of water every day. Maintaining such supplies during a siege lasting weeks or months would demand careful planning, accurate calculations, and reliable storage infrastructure. The fact that Srebrenik functioned successfully as a fortress suggests that its builders solved this problem. The exact solution, however, remains uncertain. At first glance, Srebrenik appears irregular because it follows the natural shape of the mountain. Closer examination reveals something far more sophisticated. The walls, towers, gateways, and defensive positions were arranged to maximize visibility and defensive coverage. Approaching attackers would have been exposed to overlapping fields of fire from multiple directions. Blind spots were minimized despite the irregular terrain. Modern military architecture relies heavily on geometric calculations to optimize defensive positions. While medieval builders lacked digital modeling software, they clearly understood practical geometry. The fortress demonstrates careful consideration of elevation, angles of attack, visibility corridors, and defensive coordination. This is particularly impressive because Srebrenic's builders could not simply apply a standard design. Every wall had to adapt to a uniquely shaped rock formation. The result resembles a custom-engineered defensive machine integrated directly into the landscape. How medieval surveyors achieved such accuracy remains uncertain. They likely relied on ropes, measuring rods, plumb lines, sighting techniques, and accumulated practical knowledge. Yet, the level of optimization visible at the fortress suggests a degree of engineering expertise often underestimated in discussions of medieval technology. One of Srebrenic's most recognizable features is the bridge connecting the fortress to the surrounding terrain. Today, visitors cross a stone bridge, but historians suspect that the original defensive arrangement may have been significantly different. Many medieval fortresses employed wooden drawbridges, removable bridge sections, or complex gate systems designed to isolate the stronghold during attacks. If similar systems existed at Srebrenic, much of the evidence has disappeared. This creates an important archaeological problem. The visible fortress may represent only part of the original defensive network. Critical military technologies could have been constructed primarily from timber. It rarely survives for centuries. The result is a fortress whose most advanced defensive components may no longer exist. Researchers can study the stone structures, but the complete system remains partially hidden by time. Legends surrounding Srebrenic frequently mention secret tunnels, hidden passages, and underground chambers. Such stories are common among medieval fortresses, but they often originate from real architectural features. Many fortified sites incorporated escape routes, storage rooms, concealed corridors, and protected communication passages. Limited investigations at Srebrenic have identified cavities and structural spaces within the rock formation, yet comprehensive subsurface mapping remains incomplete. Modern technologies such as ground-penetrating radar, laser scanning, and three-dimensional geological modelling have transformed archaeological research. Nevertheless, large portions of the fortress's subsurface environment remain insufficiently explored. If additional underground structures exist, they could fundamentally change our understanding of how the fortress operated during wartime. They might reveal hidden storage systems, emergency exits, water infrastructure, or construction methods currently unknown.
Sanai Maruyama, located in Aomori Prefecture in northern Japan, remained hidden beneath the ground for thousands of years until large-scale excavations began in 1992 during preparations for a baseball stadium. Archaeologists expected to find scattered prehistoric remains. Instead, they uncovered one of the largest and most sophisticated settlements ever discovered from the Jomon period. Radiocarbon dating placed the site between approximately 3900 and 2200 BCE, meaning the settlement flourished for more than 15 centuries. Even more surprising, this community existed at roughly the same time that the earliest Egyptian pyramids were being planned, and centuries before many of the great civilizations traditionally associated with advanced engineering. What researchers found challenged long-standing assumptions about what prehistoric hunter-gatherer societies were capable of building. Among the most puzzling discoveries at Sanai Maruyama were 6 enormous post holes arranged in 2 parallel rows. Each hole measured roughly 2 meters in diameter and was spaced with remarkable regularity. Archaeologists concluded that they once held massive chestnut pillars approaching 1 meter in diameter. Based on the dimensions of the post holes, modern reconstructions suggest that the original structure may have stood between 15 and 20 meters tall. To understand how extraordinary that is, consider that a 20-meter wooden structure is roughly the height of a modern 6-story building. Yet the people who built it possessed no iron tools, no steel saws, no cranes, and no wheeled vehicles, experimental archaeology has demonstrated that felling a single large chestnut tree using polished stone axes can require many hours of labour. Transporting dozens of such trees over uneven terrain would have demanded enormous coordination. The engineering challenge becomes even greater when considering the need to raise multi-ton pillars into perfectly aligned positions. Researchers still debate the purpose of the structure. Some believe it functioned as a watchtower overlooking the surrounding landscape. Others propose that it served ceremonial purposes or acted as a symbol of communal authority. A few researchers have even suggested astronomical functions because of its unusual layout. Yet no theory fully explains why such a massive investment of labour was necessary. The structure remains one of the greatest architectural mysteries in prehistoric Japan. The giant pillars reveal another puzzle. Chestnut wood was not chosen randomly. Analysis of pollen and botanical remains suggests that chestnut trees were unusually abundant around Sanai Maruyama. This discovery has led some researchers to propose that the inhabitants actively managed forests on a large scale. If true, the implications are profound. Rather than simply gathering resources from the wild, these people may have deliberately encouraged the growth of chestnut groves over generations. Such behavior resembles a form of proto-forestry. In modern forestry, long-term planning can require decades before trees reach maturity. Some of the chestnut trees used in construction may have taken 50 to 100 years to reach suitable size. This raises a remarkable question. How did a society without writing, centralized government, or recorded engineering manuals organize resource management across multiple generations? The evidence suggests planning horizons measured not in years but in lifetimes. Compared to many contemporary Neolithic communities elsewhere in the world, Sanai Maruyama appears unusually sophisticated in its relationship with the environment. The site challenges the traditional distinction between hunter-gatherers and agricultural societies. Northern Japan experiences harsh winters. Snowfall in parts of Aomori Prefecture can exceed several meters annually. High humidity, seasonal temperature fluctuations, and biological decay create difficult conditions for wooden structures. Yet many wooden remains at Sanai Maruyama survived long enough to leave exceptionally clear archaeological traces. One reason may lie in the material itself. Chestnut wood contains high concentrations of tannins, natural compounds that improve resistance to insects and rot. Modern engineers still value chestnut for outdoor construction because of these properties. What remains uncertain is whether the selection of chestnut represented accidental preference or sophisticated material knowledge accumulated through centuries of observation. If generations of builders systematically chose chestnut because it lasted longer than other species, they were effectively practicing an early form of materials engineering. This possibility becomes even more intriguing when considering the scale of construction at the site. Multiple large buildings, storage structures, and communal facilities indicate repeated use of the same material choices over many centuries. Perhaps the most surprising aspect of Sanai Maruyama is its organization. The settlement covered approximately 40 hectares. Excavations revealed hundreds of pit dwellings, longhouses, storage buildings, workshops, burial areas, and ceremonial spaces. These features were not distributed randomly across the landscape. Different activities appear concentrated in distinct zones. Residential areas were separated from storage facilities. Burial locations followed recognizable patterns. Large communal structures occupied strategically significant positions. This level of organization resembles urban planning, yet the site predates what many historians would classify as true cities. When compared with early settlements in Europe or many contemporary communities in East Asia, Sanai Maruyama demonstrates an unexpectedly complex use of space. The planning required to maintain such an arrangement for more than 1,000 years suggests social coordination far beyond what researchers once expected from prehistoric societies. The mystery is not merely how the settlement was arranged. The deeper mystery is how generations maintained that arrangement without maps, written regulations, or formal administrative systems. For many years, scholars believed Jomon communities lived relatively isolated lives. Discoveries at Sanai Mariama forced a major revision of that assumption. Excavations uncovered jade ornaments, obsidian tools, amber artifacts, and exotic materials originating far beyond the local region. Geological analysis allows researchers to identify the sources of many of these materials with remarkable precision. Some obsidian appears to have travelled hundreds of kilometres before reaching the settlement. Jade likely originated from distant sources along the Sea of Japan coast. Such distances are significant even by modern standards. Transporting materials across mountains, rivers, forests, and coastlines without roads or wheeled vehicles would have required extensive networks of exchange. The existence of these networks raises difficult questions. How were relationships maintained between distant communities? How was information transmitted across such vast regions? And how did people navigate long distances with sufficient accuracy to sustain reliable exchange for centuries? The answers remain largely unknown. One of the oldest assumptions about prehistoric hunter-gatherers is that food shortages limited population growth and settlement size. Sanai Mariama challenges this assumption. Archaeologists recovered enormous quantities of food remains, including fish bones, shellfish, nuts, fruits, animal remains, and plant materials. The diversity of resources suggests a remarkably resilient food system. Storage pits discovered throughout the settlement indicate long-term preservation of food supplies. Some storage features were carefully designed to reduce moisture and maintain stable conditions. Researchers estimate that the settlement may have supported several hundred inhabitants at its peak. Maintaining such a population for centuries would have required sophisticated knowledge of seasonal cycles, ecological management, and resource distribution. Unlike agricultural civilizations that relied heavily on a few staple crops, the inhabitants of Sanai Mariama appear to have developed a highly diversified subsistence strategy. Exactly how they balance these resources so successfully remains a topic of ongoing research. What do you think was the true purpose of the giant six-pillar structure at Sanai Mariama? Share your theory in the comments below.
Augusta Traiana lies beneath the modern city of Stara Zagora in central Bulgaria and remains one of the most remarkable Roman archaeological sites in the Balkans. Archaeologists first identified significant remains during 19th century construction projects, while systematic excavations throughout the 20th century revealed forums, streets, public buildings, water systems, and defensive structures. Yet beneath these ruins lies a technological mystery that continues to challenge researchers. How did Roman engineers create and maintain such a highly organized urban center in a region exposed to earthquakes, invasions, and centuries of environmental change, while leaving behind engineering solutions that are still not fully understood today? The visible ruins of Augusta Traiana represent only a fraction of the original city. Founded during the reign of Emperor Trajan in the early 2nd century AD, the settlement grew into one of the most important Roman centres in the Balkans. Archaeological surveys suggest that large portions of the ancient city remain hidden beneath modern development. What researchers have already uncovered reveals a level of planning and technical sophistication that raises important questions about Roman engineering capabilities. One of the most striking discoveries at Augusta Traiana is the remarkable precision of its street network. Excavations have revealed major roads intersecting at nearly perfect right angles, forming a carefully organized urban grid. Such layouts were common in Roman cities, Yet the execution at Augusta Traiana remains impressive because the builders achieved this precision across a large urban area without modern surveying instruments. Today, engineers rely on laser rangefinders, satellite positioning systems, and digital mapping software. Roman surveyors possessed none of these technologies. Instead, they worked with simple instruments such as the groma, measuring rods, plumb lines, and astronomical observations. Despite these limitations, the alignment of streets, public squares, and major buildings demonstrates an extraordinary level of accuracy. The challenge becomes even more significant when considering scale. Maintaining angular consistency across several hectares requires cumulative measurement and errors to remain extremely small. Modern civil engineers recognize how quickly tiny inaccuracies can multiply during large construction projects. Yet Augusta Traiana displays a degree of geometric control that suggests Roman surveyors possessed highly refined field methods whose practical details remain only partially understood. Every large Roman city depended on water. Public baths, fountains, workshops, households, and sanitation systems required enormous quantities of clean water every day. Augusta Traiana was no exception. However, one of the greatest mysteries concerns how engineers managed water distribution with such efficiency. Archaeological excavations have uncovered portions of pipelines, drainage channels, reservoirs, and underground conduits. These systems relied entirely on gravity. No electric pumps existed. No computerized monitoring systems regulated flow. Every gradient had to be calculated manually. Even a small mistake could cause water stagnation, flooding, or system failure. Yet many Roman hydraulic systems functioned successfully for centuries. Some surviving channels at Augusta Traiana display gradients so carefully controlled that modern engineers still study Roman hydraulic design principles for comparison. The mystery deepens because researchers have not yet identified every component of the original network. Geophysical surveys indicate that substantial underground structures remain undiscovered beneath the modern city. Some archaeologists suspect that additional reservoirs, distribution tanks, or pressure regulation systems may still lie hidden. Until those structures are found, the complete hydraulic design remains unknown. If supplying water was difficult, removing it may have been even harder. Beneath Augusta Traiana lies an extensive drainage system constructed from stone, brick, and mortar. The network carried wastewater away from streets, homes, workshops, and public facilities. In some areas, archaeologists discovered channels large enough for maintenance access. The engineering challenge involved maintaining consistent flow over long distances. Modern drainage systems depend on sophisticated calculations, computer modeling, and precision equipment. Roman engineers achieved comparable functionality using simple tools and empirical knowledge. Many drainage channels remain structurally intact despite nearly 2,000 years of earthquakes, seasonal flooding, soil movement, and urban development. Some sections continue to demonstrate remarkable resistance to collapse. Researchers still debate how Roman builders determined optimal slopes across such large areas. The answer likely involved a combination of surveying techniques, accumulated engineering knowledge, and practical experimentation. Yet the exact procedures remain largely speculative because surviving technical documentation is incomplete. The Balkan region has experienced numerous seismic events throughout history. Historical records indicate that major earthquakes affected many cities across the region during Roman and post-Roman periods. This raises an important question. Why did portions of Augusta Traiana survive? Excavated foundations reveal complex construction methods involving layered materials, stone reinforcements, and concrete cores. In some structures, builders appear to have combined different materials strategically to distribute loads and absorb stress. Modern earthquake-resistant construction often relies on flexibility rather than absolute rigidity. Interestingly, some Roman structures display characteristics consistent with this principle. Certain walls exhibit evidence of controlled deformation rather than catastrophic failure. The mystery is not whether Roman engineers understood seismic mechanics in a scientific sense. They almost certainly did not possess modern geological theory. The mystery is whether centuries of practical observation allowed them to develop construction techniques that inadvertently improved earthquake resistance. Comparisons with other Roman sites such as Pompeii, Ephesus, and cities throughout Anatolia suggest that regional builders may have adapted their methods according to local conditions. Augusta Traiana could represent one example of this lost practical engineering knowledge. Perhaps no aspect of Roman engineering generates more scientific interest today than construction materials. Concrete, mortar, brick, and stone from Augusta Traiana continue to survive after nearly 19 centuries. Modern reinforced concrete structures often require major repairs within decades, yet many Roman structures remain recognizable after 2 millennia. Laboratory analyses of Roman mortars have revealed highly complex mineral compositions. Chemical reactions between lime, volcanic materials, and aggregates sometimes produced self-strengthening properties over time. Researchers studying ancient Roman concrete have identified mineral formations capable of increasing durability rather than reducing it. Although Augusta Traiana did not use the same materials as coastal Roman harbours, its construction demonstrates comparable longevity. Scientists continue investigating whether regional variations in Roman mortar recipes contributed to exceptional durability. The unanswered question is how much Roman builders truly understood about the chemical processes involved. Were these mixtures the result of scientific knowledge, practical experimentation, or generations of accumulated craftsmanship? No definitive answer exists. Unlike archaeological sites abandoned centuries ago, Augusta Traiana remains buried beneath a living city. This creates one of the greatest challenges in Roman archaeology. Excavations can only occur in limited areas. Vast portions of the ancient city remain inaccessible beneath roads, buildings, and modern infrastructure. Ground-penetrating radar, magnetometry, and geophysical imaging have revealed anomalies indicating buried structures across large sections of Stara Zagora. These may include additional public buildings, workshops, warehouses, residential districts, and sections of infrastructure. The scale of the hidden remains suggests that current knowledge represents only a fraction of the original city. Future discoveries could dramatically change existing interpretations of Roman urban engineering in the Balkans. In some respects, Augusta Traiana resembles a giant archaeological puzzle in which most pieces remain concealed underground. Researchers can observe fragments of the design, but not the complete picture.
In southwestern Albania, roughly 12 kilometers from the Adriatic coast, lies Apollonia, hidden among rolling hills overlooking what was once a navigable river system. It was one of the largest ancient cities ever established in the Western Balkans, founded by Greek colonists from Corinth and Corcyra around 588 BC. Apollonia flourished for nearly 1,000 years before gradually fading into obscurity. Its ruins were never completely forgotten, but systematic archaeological investigations only began during the 19th and 20th centuries. Excavations revealed an enormous urban centre, covering approximately 137 hectares, where monumental temples, administrative buildings, theatres, roads, fortifications, drainage systems, workshops and residential districts emerged from the soil. What archaeologists expected to find was another successful Greek colony, but what they discovered instead was evidence of engineering knowledge that still raises difficult questions today. The greatest mystery of Apollonia is not who built it. The mystery is how ancient engineers managed to create and sustain such a sophisticated city using technologies that supposedly should have imposed severe limitations. The first mystery begins with geography. Ancient cities succeeded or failed largely because of location, as a poor choice could result in flooding, drought, famine, isolation, or military vulnerability. Apollonia appears to have avoided nearly all of these problems. The city was positioned near the Vjosa river system, one of Europe's last major wild rivers, providing access to fresh water, fertile agricultural land, transportation routes, and maritime trade through the nearby Adriatic Sea. Yet the location presents a paradox. River floodplains are notoriously unstable environments, where sediments shift constantly, channels migrate, groundwater levels fluctuate, and seasonal flooding can destroy infrastructure. Modern civil engineers conduct extensive geotechnical surveys before building large urban developments in such environments, but the founders of Apollonia had none of these tools. Nevertheless, archaeological and geological studies indicate that they selected terrain elevated enough to reduce flooding risk while remaining close enough to exploit the river network. The precision of this decision becomes even more remarkable when viewed over centuries rather than decades. Many ancient settlements were abandoned because environmental conditions changed, yet Apollonia thrived for almost a millennium. How did its planners evaluate terrain stability, drainage characteristics, and long-term environmental behavior without modern geological science? No surviving document explains their methods. Today, Apollonia stands inland. In antiquity, however, it functioned as a major commercial centre connected to maritime trade. Ancient writers described ships reaching the city through waterways linked to the Adriatic, creating one of the site's most intriguing mysteries: where exactly was the harbour? Geological evidence suggests that river sedimentation gradually altered the landscape. Over centuries, enormous quantities of sediment accumulated, transforming navigable waterways into marshes and eventually dry land. Researchers estimate that river systems can transport millions of tons of sediment annually, and even small changes accumulate dramatically over centuries. Yet, Apollonia remained an important trading centre throughout much of its history. This raises difficult engineering questions. Did ancient planners actively manage waterways? Did they dredge channels? Did they construct embankments or hydraulic structures? Some evidence suggests significant landscape modification, but the full system has never been reconstructed. The disappearance of the harbour infrastructure represents one of the greatest unsolved puzzles of the city, as entire transportation networks appear to have vanished beneath layers of geological change. No large ancient city could survive without reliable water management. Apollonia housed thousands of inhabitants, with some estimates placing the population at more than 10,000 during its peak, while others suggest significantly higher numbers. Such populations require enormous volumes of water. Archaeologists have identified drainage systems, channels, reservoirs, and hydraulic features throughout the site. At first glance, this may seem ordinary, but in reality, water engineering is among the most complex challenges any civilization faces. Modern engineers use mathematical models to calculate flow rates, pressure variations, erosion risks, and drainage capacity, whereas ancient builders relied entirely on observation and experience. Yet many ancient hydraulic systems performed remarkably well. Roman aqueducts maintained gradients as small as a few centimetres per kilometre, and some operated successfully for centuries. Apollonia presents a similar mystery. How did its engineers determine optimal slopes? How did they predict seasonal runoff? How did they prevent sediment accumulation? Even small errors can render drainage networks ineffective. The continued functionality of these systems over generations suggests a level of practical hydrological knowledge that remains poorly understood. Viewed from above, Apollonia reveals evidence of deliberate urban organization. Roads, public spaces, civic structures, and residential districts were not distributed randomly. They formed part of a coherent plan. Creating such a city required accurate surveying. Today, surveyors employ satellites, laser scanners, GPS systems, and digital mapping software. But ancient engineers possessed none of these technologies. Yet Greek urban planners frequently achieved astonishing precision. The famous city of Priene in western Anatolia demonstrates street alignments accurate enough to impress modern architects, and Apollonia appears to belong to this same tradition. Researchers continue to debate the exact methods used. Were measurements based on astronomical observations? Did surveyors employ geometric instruments now lost to history? How were large-scale alignments maintained across expanding districts? No technical manuals survive to answer these questions. The city itself remains the only surviving evidence of the knowledge behind its design. The monumental structures of Apollonia required extraordinary quantities of construction material. Columns, foundations, walls, stairways, temples, and public buildings consumed thousands of tons of stone. Transporting such material was an immense logistical challenge. Even today, moving multi-ton blocks requires cranes, heavy vehicles, and sophisticated planning. Ancient builders relied on human labour, animals, ropes, wooden sledges, and mechanical systems whose details remain uncertain. Experimental archaeologists have demonstrated that surprisingly large stones can be moved using relatively simple technologies. However, scaling these methods to support the construction of an entire city remains difficult. The challenge becomes even greater when considering timelines, as large public projects often had to be completed within political or economic constraints. How were labour forces organised? How were transportation routes maintained? How were materials distributed across construction sites? These questions remain largely unanswered. Perhaps the most overlooked mystery concerns the materials themselves. Many structures at Apollonia survived more than 2,000 years of weathering, earthquakes, biological growth, and environmental change. Their survival reflects more than architecture. It reflects material science. Researchers studying ancient construction materials repeatedly encounter unexpected sophistication. Roman marine concrete remains durable after nearly 2 millennia of exposure to seawater, and recent microscopic analysis has revealed self-healing properties within some Roman concrete mixtures. Ancient builders clearly possessed practical knowledge of chemistry, even if they lacked modern scientific terminology. Apollonia raises similar questions. What aggregate mixtures were used? How were mortars prepared? How were raw materials selected? The recipes have largely disappeared. The structures remain, but the knowledge behind them does not. Some researchers have proposed that certain ancient urban layouts incorporated astronomical considerations. The idea remains controversial. Nevertheless, examples from around the ancient world demonstrate remarkable alignments. Stonehenge aligns with solstitial events. Numerous Egyptian monuments exhibit astronomical orientations, and several Greek sanctuaries appear connected to celestial observations. Could Apollonia contain similar features? Some alignments have attracted scholarly attention, but definitive evidence remains elusive. If astronomical planning played a role, it would imply yet another layer of technical sophistication involving geometry, observation, and long-term record keeping. The question remains open. Frankfurti Cave sits on the coast of the Argolid Peninsula in southern Greece. Yet hidden inside this unremarkable limestone cave is evidence that may force historians to rethink the technological capabilities of prehistoric humans. Long before the pyramids, long before Stonehenge, and thousands of years before the first known Mediterranean civilizations, somebody living here was crossing open seas, navigating vast distances, and transporting valuable materials across the Aegean. The mystery is not that they survived. The mystery is how they did it. Archaeological excavations conducted between 1967 and 1979 revealed one of the longest continuous records of human occupation ever discovered in Europe. The cave preserves evidence spanning nearly 30,000 years, from roughly 38,000 BC to 3000 BC. Among the countless artifacts recovered, one category of material shocked researchers more than any other: volcanic glass, obsidian, and it came from an island that should have been unreachable. Franchthy Cave contains thousands of obsidian tools and fragments. Chemical analysis revealed that much of this material originated from the island of Milos in the Aegean Sea. Today, Milos lies approximately 150 kilometers from Franchthy by water. Even during the last ice age, when sea levels were significantly lower, Milos remained an island separated from mainland Greece by open water. This creates a remarkable problem. Obsidian appears at Franchthy as early as approximately 13,000 years ago. That means prehistoric hunter-gatherers were somehow reaching an island located beyond the visible horizon, extracting volcanic glass and transporting it back across the sea. This was not a one-time event. The quantity of obsidian found in later layers suggests repeated journeys over many generations. To appreciate the significance of this achievement, consider that the earliest accepted evidence of organised seafaring in many parts of Europe appears much later. The people of Franchthy may have been operating one of the oldest known maritime networks in the Mediterranean. Yet no boats survived, no harbours survived, and no navigation manuals survived. Only the obsidian remains, and it proves that somebody repeatedly crossed the sea. This may be the greatest mystery of Franchthy Cave. Reaching Milos was difficult. Finding the way back was even more difficult. Modern sailors rely on compasses, maps, GPS satellites, weather forecasts, and centuries of accumulated nautical knowledge. The inhabitants of Franchthy possessed none of these tools, yet they somehow travelled across waters that could easily become deadly. The fundamental question remains unanswered. How did they navigate? The curvature of the Earth creates a major challenge. At sea level, the visible horizon is only about 5 kilometers away. Even elevated islands disappear below the horizon at surprisingly short distances. In many conditions, sailors leaving one island could quickly lose sight of land altogether. Once surrounded by open water, there would be no obvious reference points. A minor navigational error of only a few degrees could result in missing a small island by many kilometers. Researchers have proposed several possibilities. One theory suggests that prehistoric sailors used the sun as a directional guide. The position of sunrise and sunset changes throughout the year, but experienced observers could potentially estimate direction with surprising accuracy. Another possibility involves celestial navigation. Long before written astronomy existed, humans may have learned to use recurring star patterns as orientation markers. Polynesian navigators crossed thousands of kilometers of Pacific Ocean using stars, wave patterns, cloud formations, and bird behavior without instruments. Some researchers wonder whether a simpler version of this knowledge existed in the prehistoric Aegean. A third possibility involves sea state observation. Modern indigenous navigators can detect subtle wave reflections caused by distant islands that remain invisible beyond the horizon. Certain wave patterns bend around land masses and create recognizable interference signatures. Could prehistoric sailors have learned to interpret these signals? No one knows. Even more puzzling is the question of knowledge transmission. A successful voyage could not depend entirely on luck. The same routes appear to have been used repeatedly over centuries. This implies that navigational knowledge was being taught, preserved, and passed between generations. But there was no writing, no charts, no maps, and no recorded instructions. The entire system existed only inside human memory. If Franchthy's sailors truly crossed the Aegean regularly,
They may have possessed one of the oldest sophisticated navigation traditions ever developed, and almost every detail of that tradition has vanished. The obsidian itself suggests something even more surprising: trade, or at least exchange. Obtaining obsidian required knowledge of distant locations, transporting it required planning, distributing it required social connections. This raises an extraordinary possibility. The Aegean Sea might already have contained a network of interacting communities thousands of years before the rise of classical Greek civilization. For decades, archaeologists viewed prehistoric hunter-gatherers as isolated groups with limited geographic reach. Franchthi challenges that assumption. The cave suggests movement across hundreds of kilometers of coastline and sea. In effect, the Mediterranean may already have been functioning as a communication corridor long before cities existed. Franchthi also records one of the most dramatic environmental transformations in human history. Around 20,000 years ago, global sea levels were more than 120 meters lower than today. As glaciers melted, coastlines shifted dramatically. Entire landscapes disappeared beneath rising waters. Harbours vanished. Migration routes changed. Ecosystems transformed. Yet the inhabitants of Franchthi adapted successfully. They altered hunting strategies, exploited marine resources more intensively, and adjusted to changing environments over thousands of years. The remarkable question is how they tracked these environmental changes without scientific instruments. Their survival suggests generations of accumulated ecological knowledge. In many ways, they were conducting long-term environmental observation programs spanning centuries. Excavations have revealed evidence for the exploitation of large pelagic fish, including tuna. This discovery has major implications. Tuna are not easy coastal prey. Many species migrate seasonally and often travel through deeper offshore waters. Successfully targeting them requires timing, planning, and detailed knowledge of marine behaviour. Modern fisheries rely on sonar, satellite tracking, and biological surveys. The people of Franchthi relied solely on observation, yet they managed to exploit resources that demanded a surprisingly sophisticated understanding of the sea. Some archaeologists describe this as a form of prehistoric applied science. Not science written in books, but science stored in experience. Perhaps the greatest mystery is not the voyages themselves. It is the disappearance of the knowledge that made those voyages possible. The inhabitants of Franchthi understood navigation, marine ecology, resource management, tool production, and long-distance procurement. These were not simple survival skills. They represented an accumulated body of practical expertise developed across countless generations. Yet almost none of that knowledge survives. What do you think was the secret behind Franchthi's ancient seafarers? Their boats, their navigation skills, or a lost system of knowledge we no longer understand? Share your thoughts in the comments below. Southern Albania, a long ridge overlooking the Drino Valley. Hidden beneath centuries of vegetation and abandonment stood the ruins of Phoenix, once the largest city of ancient Epirus. Archaeological investigations beginning in the 19th century and continuing through modern Italian and Albanian excavations revealed an enormous fortified city covering more than 50 hectares. Massive stone walls, public buildings, temples, reservoirs, and one of the largest theatres in the region emerged from the earth. What archaeologists expected to find was another ancient city. What they found instead was evidence of engineering capabilities that remain only partially understood. More than 2,300 years ago, the builders of Phoenix transformed a rugged mountain ridge into a heavily fortified urban centre capable of supporting thousands of inhabitants. Today, the ruins continue to raise questions about construction, methods, surveying techniques, logistics, water management, and architectural knowledge that historians still cannot fully explain.
The first mystery begins with geography. Phoenice occupies one of the most strategically advantageous locations in the Balkans. The city sits roughly 270 meters above sea level, commanding views across the surrounding valleys and major travel corridors. From its elevated position, inhabitants could monitor movement for many kilometers in multiple directions. At first glance, this may seem like an obvious military choice. The mystery is how accurately ancient planners identified the location's advantages long before aerial mapping, satellite imagery, or modern topographic analysis existed. Modern military planners use computer-generated terrain models to evaluate visibility and defensive potential. Yet, studies of Phoenice suggest its builders selected a position that maximized observation while minimizing vulnerability. Comparable examples exist at Mycenae in Greece, Masada in Israel, and Machu Picchu in Peru. However, Phoenice's ridgetop position appears particularly optimized for regional control. Archaeologists continue to debate whether ancient surveyors relied solely on direct observation or possessed more sophisticated methods of landscape analysis that have disappeared from history. The most striking feature of Phoenice is its enormous defensive wall system. Some sections extend for several kilometers around the city. The walls consist of massive limestone blocks fitted together using polygonal masonry, a technique in which irregular stones are carefully shaped to interlock with extraordinary precision. Many individual blocks weigh several tons. What puzzles engineers is the accuracy. Modern measurements show that numerous joints fit so tightly that only extremely thin gaps remain between adjacent stones. This level of precision required repeated shaping, testing, adjustment, and repositioning. The challenge becomes even more impressive when considering the tools available. The builders possessed no steel cutting equipment, hydraulic machinery, powered cranes, or laser-guided measuring systems. Yet the finished result rivals masonry seen at Mycenae, Tiryns, and even certain Inca structures such as Sacsayhuaman. Experimental archaeologists attempting to recreate polygonal masonry have discovered that achieving such precision is extraordinarily labour-intensive. Even with modern tools, producing perfectly fitted stone joints requires significant expertise. This raises an unanswered question. How did Phoenice's builders develop and maintain such advanced stoneworking knowledge across multiple generations? No technical manuals survive. No construction records survive. Only the stones remain. The walls create another engineering puzzle. Before the stones could be assembled, they first had to reach the construction site. Researchers estimate that many blocks weigh between 2 and 5 tons, while some may exceed 10 tons. Transporting such masses uphill across rugged terrain represents a major logistical challenge even today. The nearest quarries provided suitable limestone, but moving thousands of tons of material from quarry to ridgetop city would have required a highly organized workforce. Ancient Egyptian builders transported blocks for the pyramids using sledges, ramps, and large labor teams. Roman engineers employed sophisticated lifting devices powered by pulleys and treadwheel cranes. For Phoenice, the exact methods remain uncertain. Very little physical evidence survives for the transportation infrastructure that must once have existed. Were temporary roads constructed? Were wooden rollers used? Did seasonal weather conditions influence construction schedules? The answers remain largely unknown. Southern Albania lies within a seismically active region. Over the last 2 millennia, the area has experienced numerous earthquakes capable of damaging or destroying stone structures. Yet substantial portions of Phoenice's walls remain standing. This survival has attracted increasing attention from structural engineers. One possible explanation involves the polygonal masonry itself. Unlike rigid modern concrete walls, Polygonal structures distribute stress through multiple contact points. During seismic activity, slight movement can occur without immediately producing catastrophic failure. Researchers studying Inca architecture in Peru have observed similar behaviour. Some Inca walls survived major earthquakes that damaged later colonial buildings. Finis may represent another example of this phenomenon. The mystery is whether the builders intentionally designed for seismic resilience or accidentally discovered principles that modern engineering would only later formalize mathematically. No written evidence currently provides a definitive answer. A city cannot survive without water. Finis presents a significant challenge because of its elevated position. Transporting water uphill on a daily basis would have been inefficient and impractical for a large urban population. Excavations have revealed reservoirs, cisterns, and water storage systems distributed throughout the city. These discoveries demonstrate careful planning. The annual rainfall of southern Albania averages approximately 1,000 millimeters. While substantial, rainfall alone cannot guarantee a stable supply throughout seasonal fluctuations. The builders therefore needed systems capable of collecting, storing, and distributing water efficiently. Comparisons have been made with Petra in Jordan, where Nabatean engineers developed sophisticated water harvesting technologies, and with ancient Pergamon in Anatolia, whose inhabitants constructed advanced hydraulic systems. Finis appears less technologically dramatic than those sites. Yet many details remain poorly understood. How much water could the reservoir store? How were losses from evaporation minimized? How was water quality maintained? Researchers continue investigating these questions. One of the most surprising discoveries at Finis is the scale of urban organization. The city included residential districts, administrative structures, religious buildings, storage facilities, public spaces, and a large theatre. Constructing such a complex settlement on uneven terrain required extensive planning. Today, urban planners rely on digital terrain models, engineering software, and geographic information systems. Ancient planners had none of these tools, yet Finis demonstrates careful integration between architecture and landscape. Roads connect different sectors efficiently. Major structures occupy advantageous positions. Defensive considerations appear integrated into the city's overall design. The result suggests a level of planning sophistication that exceeds common assumptions about regional settlements during the Hellenistic period. Among Finis's most remarkable structures is its theatre. The theatre ranks among the largest ancient theatres discovered in the region and could accommodate thousands of spectators. Like many Greek theatres, it raises questions about ancient acoustic knowledge. Modern acoustic engineers use mathematical modelling, computer simulations, and advanced materials testing to optimize sound transmission. Ancient builders possessed none of these resources, yet performances remained intelligible to audiences seated considerable distances from the stage. Research conducted at comparable Greek theatres has demonstrated that architectural geometry can naturally amplify certain frequencies associated with human speech. Whether ancient architects understood these principles theoretically or discovered them through centuries of experimentation remains uncertain. Finis may preserve evidence of one of the world's earliest forms of large-scale acoustic engineering. The city itself poses a final logistical question. Finis was not a small village. At its peak, it served as a major political and economic centre for the Chaonians and later played an important role within the broader Hellenistic and Roman worlds. Large-scale construction projects require resources. Stone must be quarried, workers must be fed, tools must be manufactured, infrastructure must be maintained. All of this implies a sophisticated economic network. Archaeological evidence suggests connections extending throughout Epirus and beyond. Trade routes linked the city with coastal regions, inland communities, and Mediterranean markets. Yet, historians still debate the true scale of Phoenix's economy. How large was its population? How many workers participated in major construction projects? How were labour forces organised? The archaeological record provides clues, but not complete answers.